So we'll start today's session by revising a bit what we did. So initially we discussed about what computational graphs are. So if we have an expression, we have to make a computational graph out of that. And after that we did forward pass, and then we did manual backpropagation. So some rules of thumb. The first rule is that if you have addition, so let's suppose if you have a plus b, you have an expression of this sort, and this gave rise to suppose c. So when you make a computational graph, it will become like something like this: a, b, and this gave rise to c. Now you know that this can be embedded in a huge computational graph. Suppose this expression is part of some bigger expression. So here you can have a lot of other neurons and other things. And once you reach, suppose this c, if you reach this c, so you will compute gradient. Suppose you compute a gradient somehow. So you know that c dot grad is computed. Now in order to compute this gradient of a and b, so you know the rules. In case of addition, you will just shift the gradient. You will just relate the gradient. So what will happen is you will say that a dot grad is equal to c dot grad. So whatever gradient you computed, in case of addition, you will just distribute the gradient. You will take this gradient and give it to this a, and similarly you will do b dot grad, that also will be equal to c dot grad. So this is the rule number one. In case of addition, this is what you do. So when you have an addition node in between, you have two nodes and it's giving rise to third node, and you have already computed the c dot grad. So what will happen is you just have to give the gradient to other nodes. You will just back propagate it in a way. Rule number second. So rule number second is for multiplication. This is for multiplication. So the first rule was for addition. So this was for addition, and the second case is for multiplication. Now you have two nodes, suppose a and b, and you want to multiply them. That gives rise to suppose a node c. So in this case, again, this can be embedded in a huge computational graph, and what you have to do is you assume that you have computed c dot grad, and now what will happen here is if you have to compute a dot grad, so a dot grad will be equal to, you will take this c dot grad, basically the global gradient, and then you will have to compute local gradient. So local gradient is equal to b dot value. So you will have to multiply these two things. So in a, you will take the other nodes, whatever the other node was. Suppose you are computing a gradient for this node, you will take the value of the other node and you will take gradient of the global gradient, and you will multiply these things. And once we have done it for a, and you will do it the same thing for b. So the b dot grad will be equal to, so b dot grad, if you have computing gradient for this, now you already have computed gradient for this, so you'll again do c dot grad. This is the global gradient, and what is the local gradient? So local will be a dot value, because you know that each of this node has a couple of important things. So one important thing is its label, the name of the node, and then we have its value, okay, and then we have its gradient, and then other things are there still, children, what are the children of this node and stuff like that. But these are the things that we use in backpropagation. We use this value and the grad. So this is rule number two in case of multiplication. This is very important that you have to remember. So usually these are two operations. If you see any neuron, so that will be w transpose x plus b, or w multiply x plus b. So you will do addition and multiplication. So that's why I am telling you these two rules. And then if it's the function, or you are backpropagating through a function, then you just multiply the whatever is the global gradient multiplied by the derivative of that function. Okay, we'll use that rule as well. And one more thing that I have to tell you, if let's suppose you have a node b and it is connected to suppose multiple nodes or multiple neurons, so whatever is the gradient of these things, you have to keep on adding these gradients. The first thing is you will update the gradient of this b with respect to this node, and then with this node, then with this node, then with this node, and we have seen NF calculus, the gradient will be added continuously. So this is rule number considered as rule number 3. So when a node is there which is connected to the multiple nodes or is connected to the multiple neurons, so what you do is you will compute gradient of this, and then you will keep on adding it to this b dot grad, and same thing will happen to this, same thing will happen to this and this. So you add these gradients once you compute them in respect of the b. And then the fourth rule which I said is rule number 4. These are not hard and bound rules. I just want to make sure that you still know them. Suppose you have a node over here, and then there is a node. It's a generic rule. Suppose now this is out grad, so you have out gradient or global gradient, which can be called as global gradient. So you have this global gradient, and you have a function which you applied onto this. Suppose something happened here, and before that you applied tan h or something. So you will take the global gradient and then multiply it with the derivative of that function. Suppose if this function is f of x, so you will say the global gradient, let's see, global gradient multiplied by derivative of this function, and that's how you will set the gradient. So this is gradient of the node which is preceding it. So this is rule number 4. So if you have a node and you have other node and you had applied some function onto that, you will take the global gradient and then you multiply by the derivative of the function that was applied onto this. That's how you update the gradient. Again, I have told you 4 rules, two important rules of addition and multiplication. In addition, you just relay the gradient, you just distribute it. And in case of multiplication, there is this rule that you take the global gradient and multiply it with the local gradient, and local gradient is the value of other thing. And rule 3 is, if you have a node which is connected to the multiple nodes, that is usually the case in neurons. So what you do is, you will take the gradient of all these things. Once you compute gradient of suppose B, you will first take the gradient with respect to this and add it. With respect to second node, add, and you will keep on adding this. And rule number 4 is, if you have a node and you have applied some function to this value, so what we will do is, you will take the global gradient and then whatever function you have applied, you will take gradient of that and you will multiply it, and that's how you will update the gradient of the node in the consideration. So these are the rules. So let me now switch to the code window and just revise what are the things that we did in terms of param class, because we had created a custom data structure. Okay, so I hope that the code window is visible. So let me show you that one by one. So we started with params class. So initially I'll just copy paste so that you people will be able to revise and I can also get the updated code. The first thing was, we were doing the standard imports. I hope this is visible. So these are the standard imports that we did, and after that we have to have a params class. So this was the params class. This was our custom data structure, so in which we defined a lot of functionalities. The first thing is, we have init method, the constructor. If you see in that, what we have is, we have the data, the value, actual value, the data of this params, and then we have what are the children that it has, what are the nodes which produced it, and what is the operation that was applied to these children in order to get it, and then the label. So what is the name this node will have. So these are the things that we have, these are the attributes. And then we defined some methods. We'll define a wrapper class which was used to print the stuff. Let me copy these things as well, so that I'm just making it so that you people can revise the things that we have done so far. So if you see this, so this was the wrapper class. So this wrapper class is used when you print these things and you want to print the data, the label, operations, and the gradient. And the basic arithmetic operations were addition and then multiplication. This is what we defined. So you already know this. So the self dot data plus other dot data, and then these are the children, and this operation is plus which produced it, and we are giving the label as well here. So this is once we do add. So if you say, let's suppose if you define a value params of 2.0, params of 3.0, and you want to add these two things, and then this is what will be called internally, this add function. Similar thing will happen in multiplication. And I think we have also defined some other things. Let's also define subtraction. It won't be difficult. So if we define subtraction, so subtraction is the same thing. Oops. So what we can do is, you can define subtraction like this. So you are having self dot other, self plus minus other. So you are just negating this other operation and you are returning that. And then we can also have negation defined now, because we are negating the stuff. So what we can do is, so once we do this minus of other, so before this you can have a negation operation. So this is what will happen. So you'll have params self dot data. So you'll just negate it over here. And because it will have just self, it is a unary operation, and this is the operation minus, and you will have this label. So these are the basic methods that we defined over here. And then we also had backward, which we did not implement. Suppose now today what will we do is, if you know this, and after that we had graph utilities in which we were visualizing this. I'll just copy paste the graph utilities. Just give me some time to copy paste it. So this is the general params class, and we'll keep on adding the functionality into this. And one important thing was this graph utilities, in which we were making the graph. Okay, I think this trace of E is not required. So this was the graph trace, and we made this trace so as to get nodes and edges. And then this draw dart is responsible for taking these edges. So what will edges and nodes? So it will create a graph out of that. So this is the main code that we wrote in the previous sessions. Any questions so far? So now today what we'll discuss is, because we have already done a basic example in which we took some nodes and then we did some operation onto that. So today we'll start with a neuron. So we'll do the back propagation on a neuron. So how does a neuron look like? You already know that. So I'll make a visual representation of a neuron. So it takes some inputs. So you have inputs like this, and the inputs are also, there are weights defined to this. Suppose this is W1, this is W2, and this is W3. These are weights in the neuron, and you aggregate these things together. So you have these inputs. Suppose this is X1, this is x2 and this is x3. So you aggregate over here, suppose this is affine transformation over here, and then you apply activation. So I can write activation as ACT, and then you give some output over here. So this is the visual representation. How do we write it mathematically? So you'll say W transpose X plus this bias, and then you apply some function over here. So till here, this was aggregation or affine transformation, and over here, this is the activation function, and this is the nonlinearity, that we want to have. Now you see this, you have W1 X1, W2 X2, and then plus bias, and then you get some output over here. So this is the same thing we'll have to use, and then we'll back propagate through a single neuron, and then we'll make a layer of neurons, then we'll make a whole network. So starting with this. So now that we have already this params class is there, so what can we do is, so I'll again bring the code window back. So I'll define, the first thing that I'll define is these parameters. So I'll have W1 X1, W2 X2. So these will be the things that I defined. So now if you can see it over here, so I'll just copy paste it. So you have X1, X2, W1, W2. I'm just having a neuron which takes 2 inputs, and it will have 2 weights and a bias. So this is 2.0, 3.0, 0.5, minus 0.5, and 1.0 is the bias. So this is what I am defining. So I can just print these things also. So if I want to print the values of these things, so that I'm sure that these things are working. So now you can see that neuron leaves. So this is parameter, and I've also given labels corresponding to those things. And the gradient is initialized by default as 0. So you can check it over here. And now what I need to do is, the second thing is I'll have to do forward pass. The forward pass is X1 W1 plus X2 W2 plus bias. So this will be the forward pass. So how to compute that? The first thing is to compute this. So this is X1 W1. So I'm creating a different node, and which is made by multiplying X1 and W1. So this is the operation that I'm using, and this is now a separate node. Similar thing will be done to X2 W2. So now I'm doing this as well, because all these operations are defined. So if you know, so this X1 is a param, X2 is a param. So this is a data structure that we have made, and now we're multiplying these things. Okay, and now we have to add these things together. So we also have to create another node. So now this is sum of these two things. So X1 W1, whatever I created over here, and then I'm adding them together, and then I'll add bias towards that, and I'll call that Z. So one more node is there. So this is forward pass. If you see it over here, so Z is equal sum XW. So whatever I have done over here, and then I'm just adding bias to it. Okay, and this is literally what we do in a neuron in the forward pass. So I can print this intermediate values. Let me print that. So if I can print it, so you can see over here. So these are the values 1.0, minus 1.5, and the gradient is 0. So these are the intermediate values. And I'll also apply sigmoid function onto this. So let me apply sigmoid function. So how to apply sigmoid? So I'll call that out. So I'll apply sigmoid after this. So because I have this out and Z is over here, so I'll apply sigmoid onto the Z. So once I run this, I'm expecting an error. So I hope, is sigmoid defined over here somewhere? Let me run this, because sigmoid is not defined. I don't know why it's working. Yeah, so now you see the sigmoid is not defined. So now we'll have to define sigmoid over here, because I didn't run the params class initially. I think some other params class was running in which sigmoid was defined. So now you see this sigmoid is not here. So I'll have to define sigmoid. So you know what sigmoid is. So you already know the 1 divided by 1 plus e to the power minus x. So I have defined many operations. Let me define sigmoid as well now. Okay, I'll just copy paste, and I'll explain you what is happening over here. So after subtraction, I'll define one more function, and this is sigmoid. So you can see this. Oops. So if you see this over here, so sigmoid is defined like this. You have 1 divided by 1 plus e to the power minus x. This is how we have defined it. And now what I have done is I've directly used exponentiation, or I could have used exponentiation. I could have defined it within this class and then used it, but here I am importing math, so I'm using exponential from the math. So it depends on you what is the level of abstraction you want. You can have different level of abstraction. You can define exponentiation on your own and then use it, as I did with that negation. So I had to do a subtraction. So before that I introduced negation, and I used negation in the subtraction. You could have done the same thing over here. So you have exponentiation that's defined in the maths. I could have used this, or if you want to dig a level deeper, so what you can do is you can just remove this exponential from here, and you can define your exponentiation on your own within the class, and then you can use that. But here what you see is this is the definition of the sigmoid function, and I am doing same thing mathematically, 1 divided 1 plus math dot exponential of minus self dot data. Okay, and then I am converting this into the params class. Okay, now I hope that sigmoid class should work. So if I run this again do this, and now out dot g, if you see, I can also get the value out of this. You see this out. Now after application of sigmoid, you have this. Now one more thing that we have, we know that we can also draw a computation graph of this. So how to do that? So I can say draw dot, so and then this out. If I draw this, you can see this is a graph. So whatever you are seeing right now over here is a computation graph of a single neuron. So you have w1, x1, these two got multiplied, and we have a different node x1 dot x1 w1, and its data is here, and gradient is 0 for everything. So I can just show you the whole computation graph. Okay, we do not do anything new here. We just added some pieces. That is, we just applied sigmoid on this, and you can check that over here. In the last node, I'm applying sigmoid, and I'm getting sigmoid of this. So I applied sigmoid onto this, and I'm getting the data over here. Now I'll have to perform the manual backpropagation. So any questions so far? Now if you understood this, so what we did is we initially defined these params. We had these weights and biases and the input, so we defined them, and then we did the forward pass. Now we'll have to do again manual backpropagation. This is again pain, so you'll have to go through that pain once more so as to understand this. So the rules that I've taught in the initial portion of the lecture, you have to remember those rules, and then we'll make use of that. The first thing that we have over here is you have this node, that is this z node. So I have labeled it as sigmoid of this, but you already know that the node actually is named as z. So this is that node. I think this is now out because z after applying sigmoid, and we gave it out. So this node over here is out, this node. So you'll have to apply this manual backpropagation node by node. So how can we do that? So we'll start with the end node, that is this out node. So out by default, if you take derivative of out with respect to out, or consider this as loss function, this sigmoid, the whole of this can be considered now as a loss function. Derivative of loss with respect to loss is 1. So we can directly assign this out dot grad. So from here I'll do manual backpropagation again, manual backpropagation. Okay, so now the first thing that I will do is out dot grad. Out dot grad is equal to 1.0. This is the base case, because we know that derivative of loss function with respect to loss function is 1.0 is 1. So that's what I have done over here. Now we'll go to this. We'll keep on drawing this. So if I press enter over here, and then I'll see if the updations have happened. So you can see over here that gradient is equal to 1.0. Now I'm done with this node. I'm done with out node. Now I'll have to compute for this node. So this is my z node. So before going to z node, so what I'll do is, so I will consider this out dot grad. So I'll call that s. Let me do that so that my calculations become easier. So this is s is out dot data. Okay, so now I have to apply sigmoid. What did I say? If I have a node and after that I have applied some function, so what will I do? I'll take global gradient and multiply by the derivative of that function. I'll have to take derivative of the sigmoid over here. So the first thing is this out dot data is the one that I'll take into consideration, and then I will, so consider this as out dot grad is the global gradient over here. So this is out dot grad, this is the global gradient because it is coming after this. Right now whatever you're computing is gradient for this z node. So for that I'll have to compute, say we'll call it z dot grad. This is the gradient that we are computing. This is equal to z dot gradient is equal to, what is the global gradient? The global gradient that we have over here is out dot grad. This is the global gradient. I think this is rule number, I don't know what, rule number 4. So now you have this out dot grad, that is the global gradient, and multiply by, you have to take derivative of the sigmoid function. Okay, so this is the sigmoid function. And what is the derivative of sigmoid function? I'll just tell you that. Give me a second. So if you see over here, so if you have sigmoid function, sigmoid is generally represented by sigma of z, something of this sort. Okay, if you have to take derivative of this, you can compute, you know, sigmoid is 1 divided by 1 plus e to the power minus z in this case. So now if you take derivative of this, okay, so if you take derivative of this derivative will be equal to sigma of z multiplied by 1 minus sigma of z. So this is the derivative of sigmoid function. Okay, so if you have sigmoid function, the derivative of sigmoid function, so sigma dash of z is equal to this. Okay, you have to remember this. So this is the derivative of the function, and we'll use this derivative, we'll use this, and because we already know that this out dot data, so this data, this thing was already called s, this was called as s. Let me just remove the code so it's clearly visible. So you have this sigma of z, this is defined like this, 1 divided by 1 plus e to the power z. Now we take derivative of this, sigma dash of z, so this is equal to this. Okay, now we already know that the sigma of z, this is actually data, that out dot data. The out dot data was called s, so this was called as s. So what we can write is, this is equal to s multiplied by 1 minus s. So we can directly write like this. So whatever we had, the global gradient, take that and multiply with the derivative of the function. I think this was rule number, let me see, this was rule number 4. Rule number 4 was this. So if you have a node after which you have applied some function, so you will take global gradient and then multiply by the derivative of this function. That's what I'm doing over here. So I know the derivative of function is this, so I'll have to multiply this with out dot grad. That's what I'll be doing. I'll bring the code window back so that I'll do the same computation in the code. So now you can see this. So I'm saying z dot grad multiplied by s into s minus s into 1 minus s multiplied by 1 minus s, because this is the derivative of this. So this is the gradient. So we can update z dot grad like this. So I can run this again. So if I run this, so I'll have to again check it why the gradient's updated, and you can clearly see that the gradient was updated. And how to check this, I have also told you, you have numerical methods of differentiation by the help of which you can check if the gradients are correct. So how can you do that? You can just take whatever the value, you have this forward pass over here, okay, and you have these params over, you will just nudge the value. Suppose you are right now doing it with respect to some variable like this z, so you will nudge this z a bit. So how can you nudge the value of z? You will just add plus h to that, and then you will again do the forward pass. So you will have original value, and then you will have this nudged value. You will subtract them and divide by that small value, and you will basically use the definition of numerical gradient and check with this. I am not doing that, but you can still have a snippet of code that by the help of which you can check are the gradients correct, are you doing something wrong. So how to do that, I already told you that. So you are having backprop, you do that initially, and then whatever node is under consideration, suppose in this case the z node was under consideration, you have to nudge its value by h and then use the definition. What is the definition? The definition is f of x minus f of x plus h divided by h. So you can use this numerical definition to see if your gradients are correct. So this is for numerical checking, that I already told you. Okay, now let's go to some important nodes. So now let's go to this plus node. Plus nodes are quite easy, nothing to do, you just shift the gradient. Whatever was here, you can shift that. So for this b dot grad and this x1, this sum of this, we can directly say this is for node number 3. This is quite easy. This is add, you just are doing z dot grad, whatever was z dot grad, whatever is the global gradient. So global gradient is z dot grad, you are just relaying that to b dot grad and sum of xw dot grad. I should write dot grad over here. Okay, this is sum of xw is this node, this without the bias. Okay, so now I already know that I have computed gradients for this. This is 0.234, 0.2350. So I'll just relay onto this and this, to this bias and to this. So if I now press enter over here and I draw this again, so you can see that the gradients were updated. Okay, same case for the other operation. So you have again one more addition. So you have this, so you can relay the gradient again for addition. It's quite easy. Let me just copy and paste that. This should be dot grad, and this also should be dot grad. Whatever gradient I have computed, so this is the global gradient for this particular node, x1 w1 and x2 w2. For these two nodes, the global gradient comes from this. So I'm taking whatever gradient was in that node and I'm just relaying onto these two things, that transferring the gradient. This is quite easy for addition. So if I run this, if I again run this cell, so you'll see that the gradient got updated. So you got 0.234. And now is the interesting case, because we are doing it for multiplication. So for multiplication, suppose if I'm taking w1 into consideration, so I'll take global gradient, whatever the gradient was computed before it, this gradient, and multiply the other. So other in this case is x1. I'll say other of data. Okay, so I'll use rule number, I think 2. So rule number 2 will be used. So now I can just do it for all these things, x1 w1 and x2 w2. I can just copy paste it over here and explain. So I have an x dot grad. So take the global gradient, that is x1 w1, whatever came after it, okay, and then w1 of data, because we're computing gradient for x1. So we'll take the others data. Other data was w1. Similarly for w1, we'll take the global gradient, and you will see that I am multiplying it by x1 of data, that is other of data. Similar for this w2 and x2. But you can clearly see over here, I am doing plus is equal always. I am adding the gradient. As I told you, this is again a rule number 3, I suppose. So in which if there is a node which is connected to multiple nodes, so you will keep on adding the gradients, because gradient computation can happen multiple times for a node if it is connected to multiple nodes. That's why I have to keep on adding. If I just write is equal to, that will be a huge bug. Maybe it will be very difficult to recognize the bug even, because sometimes the network will turn out to be fine and it might be working, but it's taking lot time for convergence. But you know that the problem would be here. So be careful. If you have a node which is embedded in a huge graph and it is connected to multiple nodes, its gradient will be computed multiple times, and you have to add these gradients. You have to keep on adding these gradients. Otherwise, what will happen is that the computation won't happen. Okay, and if it happens, let's suppose it will just reassign the value. So you have to be very careful in this. Why am I doing this plus is equal to? Okay, so if I run this now, so I think I have done the manual backpropagation for the whole neuron. So this is over here now. So you can see all these nodes were updated. 0.94, 0.234, and all of these things over here. Okay, so any questions still here? So now you saw that what we did so far is we took a single neuron and we did manual backpropagation on the single neuron. So in order to check, so I'll just show you this in PyTorch. So let's suppose we'll print the gradient of all these neurons together. So now that we have already computed them, so we can just say print out.grad, z.grad, b.grad, all these neurons, and with intermediate neurons, I'll just print it. So you can see these are the gradients. So whatever neurons we had in the or nodes we had in the computational graph, so all of these gradients are printed over here. So let's do one thing. Let's do the same thing in PyTorch, and we'll see how is PyTorch doing it and are the values that we got agreeing with the PyTorch. So how to do that with PyTorch? Let's do that. Let's call this as tensor. So what I'll do is I'll import torch. So you know that this is how PyTorch works. So you will take import. Oops, this is not copying. Okay, now you can see this. I am saying tx1. So this is how a torch.tensor. In our case, we were saying params, and in that params we were giving some input. Let's suppose 2.0. In this we have torch.tensor. This is the general API of PyTorch. And then requires grad means do we require grad for this? So we require gradient for everything. So I'll just write true for this case and true for this case as well. So what does this mean? This means basically that you have to compute gradient for this as well. So when I'm writing requires grad is equal to true, this is one of the parameters that is coded in PyTorch. So you can see that general API remains the same. So we are writing tx1 params of this value, and then we're also giving label. So in this case you are giving 2.0, and then you are saying that requires grad is equal to true. So this is how it is done in PyTorch. And now we have to do say forward pass. So in how can we do forward pass? You can just keep on adding. So you don't need to do it separately as we did in above case. You can say tz. Tz basically means whatever is the z value. tx1 multiplied by t. This is the x1 w1 x2 w2 plus bias. So this is what we did in the params. So we did the same thing, but we did that in multiple steps. So if you see over here, so this was done in multiple steps. We could have just added them together and multiplied them in the single step. So here we are doing in the single step in PyTorch. So if you see, this is tz is equal to tx1 multiplied tw1 plus this and that. This is basically x1 w1 x2 w2 plus bias. And now what we can do is we can apply sigmoid onto this. So how is sigmoid defined? So in our case we were writing z dot sigmoid, but in PyTorch API is a little bit different. So what are they doing? They're saying torch dot sigmoid. They have defined sigmoid within torch, and it takes input as this. So t dot out is sigmoid. Okay, so you can so far just print these values. So what I can do is I can print all these values together as I printed it over here. So once I was doing this, so I was printing the values. So I can do the same thing. Or these are the forward intermediate values, and we can see if they check. I think they should easily check because we're just doing multiplications, not much. And this is tx1 w1. Oops. And I think I don't have intermediate values, so here I can just print tz and t out. Tz and t out can be calculated, and then we can compare it with. So this can be removed. So if you see this, so these are the values. So and I think you can say dot item is how you can take out the value. Dot item in PyTorch. You can write dot item over here also. So what it will do is, so it is basically that data structure, and it will pluck out this value. It will take out this value. So right now we have tensor dot something, and if we just say this thing dot item, so it will pluck out the value. So if you see this, so this is 0.5 and 0.62. So this is tz and t out. So in our case, this is out, and this is, I think, was z computed? Yes. So this is z. So this is that z 0.5 and 0.6225. I think these values agree so far. In the forward pass, it's quite easy. It's not difficult. So the main thing that we have to compute is it doing the same thing with back propagation? How to do back propagation? So we'll just compute this dot backwards, and then we'll do the back propagation. And maybe that can be done after we do the back propagation with our framework. So far we checked the forward pass and it's working, and you see that you saw the API for both of these things. It's almost looking similar. So whatever we did, we are calling it param. So here they are calling it tensor. So they are saying torch.tensor. In our case, we're just calling param. So forward passes, so agreeing with this. So now we will put the end to this suffering. So we will not manually back propagate again. So we'll have to automate this back propagation somehow. So now, so far what you saw is, you saw how can we do forward pass and manual back propagation. You also saw that it agreed with PyTorch. Forward pass is agreeing with the forward pass of the PyTorch, and there was no difference in the APIs so far. So can you confirm that you're understanding everything? Now that you understood how is manual back propagation working, so what we can do is, we will now do this autograd. Like we'll have to do all the things that we did, but it should be done automatically by the code itself. We don't have to, let's suppose, do it node by node and traverse through the whole graph. So we'll have to automate it by the code. The first thing in this that you have to do is that you should recognize, we went in this computation graph in a particular order. So if you saw this node, so you had nodes like this, and then suppose these were connected with these things, these were connected to these two, suppose they were fully connected networks. I'll just roughly make it. Consider this as fully connected network, and consider this as fully connected network. Okay, so what we did is, we started from here and we went backwards. So we went into a particular order. Okay, so this ordering is basically called as topological ordering. It's called topological sort. People from computer science will know it. If you have direct acyclic graph, which this neural network is, and then you can apply topological sort on it. So what is topological sort? You people should know it. If you don't know it, you can just search it. So basically what it does is, it will stretch out the graph, and the direction will be from one node to other. So generally, suppose if you have dependencies in the graph, suppose you're right now learning deep learning. So for deep learning, the prerequisite is machine learning. Okay, suppose for deep learning, prerequisite is coding as well, something of this sort. And for this machine learning, the prerequisites is mathematics. Okay, something of this sort. Now you see this is a directly acyclic graph. So what you can do is, if you want to stretch it out, you don't want to, you cannot start deep learning directly. You will have to do ML, and before that you will have to do mathematics, and you will have to do coding of this sort. And if you want to see what is the way in which I can cover these courses, so you can apply topological sort on it. It will basically remove the dependency. It will tell you, okay, you have to do this first, followed by this, because these things don't have dependencies, and it will be done by topological sort. So these sort of problems are done by topological sort. So what is topological sort? It is laying out the graph, and where the edges go from one end to the other. Okay, and if you have all the other, this is a very complex graph, but there should be no cycles in it. So you'll apply topological sort onto this, so it will lay down the graph, and the graph will go edge will go from, suppose, left to right. Okay, with no dependency. So you can directly start from left, and then you can directly go to right, and you will have no dependencies. This is one of the applications of topological sort. If you have to cover courses and they have dependency on each other. Suppose similarly schedules. So if there's a huge company which is doing a lot of operations. So in that, you know that before going to other department, department A and department B, suppose there are two departments, A and B is dependent on A, suppose. So before you go to department B, somehow the work of the A should be done. So there's a dependency between that. If you have such dependency graphs, so how can you remove these dependencies? So what you can do is, in order to say what is the order that I should traverse, so you can apply topological sort on that. Okay, topological sort in essence is a topic that can take 30 minutes to cover, but I hope that you people can do it on your own. Okay, it is basically depth first search, something of that sort. Any questions till here? Okay, now you know that we will use topological sort. Why will you use it? Because you saw that we were doing back propagation and we were starting from the end. So we'll use a reverse topological sort. So we'll come in the reverse way of topology. We'll come from the end, from the loss function, and go step by step. And so that now the nodes should be arranged in a certain order so that you can apply this back propagation. And now the back propagation, if you see, it will have certain rules. The first rule will be for, suppose addition will have a separate rule, multiplication will have a separate rule, the rules that we saw. Okay, and then for each of the functions, for each of the operations rather, what we can do is we should have a rule in which we'll have to set the gradient, because there are two things involved. So if it's a binary operation, suppose it's addition, multiplication, you will have two nodes which are coming together and producing third node. Okay, and while producing that, you already know that this operation behaves in a certain way, and you know the rules for that. So that's what we'll do. And we'll write the backward pass now, and then we will see what can be done. So now again going to the same code. I hope code is visible. So now we'll do the automatic differentiation. Okay, so before that, what we have to do is we will apply topological sort. So how to apply topological sort? So I'll just write the code. So suppose if you are given, this is the code for topological sort. Okay, so you will call this build on a node. Suppose this is any node. So if you are given a graph, so in our case, so the graph that we had is this graph. This is the graph that we have, the computational graph. We have drawn this graph, so we can take this out. Okay, and we will just call this topological sort. So if you see this topological sort, okay, I'll say build of out. So we'll have topo, and this topo will be a list of the nodes. It will be in topological sort, and I just want to print this topo. And this, if you see this, so these nodes were here are now in topological sort. You can clearly see initially x1, then we have w1, then we have x1, w1, because x1, w1 have dependency over x1 and w1. Then we have w2, then we have x2, then we have x2 and w2. Okay, you can see that dependencies are removed. Graph is somehow laid out. Okay, how many of you can see this? The graph was laid out. It is from x1. Now at the end you have sigmoid. So graph is laid out. You have particular ordering in this. The ordering is sort of laid out the graph that we had. Now if you see whatever node is coming after, it will have dependency what came before. Before nodes will never have a dependency on what is before it. So x1 and w1 don't have dependencies, they are first, and this x1 w1 has dependency on both x1 and w1. So now you see that this node is the third node. So this is what we have done so far. So we used topological sort. So in topological sort we just laid it out. Okay, now what we have to do is, the second thing is we'll have to have base case. So base case is gradient out.grad is 1. So this is our base case. So I'll say out.grad is 1. Oops, I'll just type out.grad is 1. Out.grad is the gradient that we have, and now we'll have automated. Okay, so after that I'll go through each of these nodes and I'll apply the gradient, and for that I'll also have to write code. So how in case of plus operation, in case of multiplication, how should the values be updated. But if you see, this is the base case, out.grad is equal to 1.0. Now what can I do is I'll just write code for all the operations that we have so far So I'll just copy and paste. So now you can see this. So you have V in reverse topo, because now we are not going in topological sort, we are going in reverse topological sort. We'll start from this, we'll start from end. Okay, so end is the base cases, out.grad is 1.0, then we'll start with this node, then we'll start with this node. So that's the order I'm going in. So I'm basically traversing this topological list, this topological topo list, which has topologically sorted these nodes, and I'm going in reverse order. And then I'm checking for operations. What is the operation that created the node? Suppose if we do operation is addition, if this is addition. So what I'm saying is, for addition, take out the children. So whatever children were there. So you had 2 children. So you had children, and then you will say you have to update gradient based on that. So what happens in that case? You will just relay the gradients. Okay, I'll just make a diagram so that it's visible. Suppose you have nodes A and you have nodes B. If the operation was addition, so this gave rise to node C. So you already have the C node. Suppose this C node is basically the gradient that already came from it. So now what will happen is, if this operation is plus, okay, so it will identify over here, and then it will say, okay, currently suppose I am at some node. Okay, I am at some node, and based on that, if you see the children that it has is A and B. So you will see A and B are the children. So A and B over here are the children. So children, V dot children. So it will traverse both of these. It will traverse A and B, and it will upgrade gradients for this. Ch dot grad is equal to whatever V dot grad, whatever grad came from. So this will be our V dot grad. Okay, because we are, let's suppose, V dot operation. So V is the vertex, or V is the node that we have. So not the vertex, V is the node. So if you see in this case, V dot children, so it will update gradient for A and then for B. And how it will update it? It will just take the gradient of this and multiply it with 1. So this is basically effectively the similar thing. So I'm just multiplying 1, because gradient of A with respect to A will be 1. So that's why I'm multiplying it with 1. Similarly, gradient of B with respect to B, local gradient is equal to 1, and global gradient is V dot grad. So this is in case of addition. In case of addition, you just take this gradient, basically out grad or V dot grad, and then you just relay on to these two things. Okay, this is what is happening. If now the operation is multiplication, suppose if this is multiplying, you know what will happen. So in this case, children will be A and B again. So I'm taking children out from this. So A and B will be the children. If you can see over here, I am just saying, let's suppose this A and B were produced by multiplication of A and B, and then the C got produced. So right now we'll say serial operation. Suppose this operation over here is multiplication. So this case will be fulfilled. And now what will happen is A comma B. So it will have children like this. So V dot children, because we already have children stored in this C. So V dot children will be A and B. So we got A and B. Now how to update A and B? We already saw the rule. A dot grad plus is equal to whatever is the global gradient. So this is global gradient and other data. So B dot data. For A it will be B dot data. For B it will be A dot data. Okay, this is in case of multiplication. Similarly for sigmoid, you already know that sigmoid, the derivative is this, but this is the derivative, s into 1 minus s, and this is multiplied by global gradient. So global gradient in this case is V dot grad, the node at which we are, and then you just multiply it with s into 1 minus s. And similarly for subtraction, you already know that you just have to multiply it by minus 1. So in case of subtraction, the same thing applies, but with negative sign. So whatever we did in addition. Everything clear so far? So how did we write these rules? So these were the 4 rules that we discussed. Now that you saw this, so what can we do is, so we can use this. So we'll just run this, and then hopefully that gradients were updated automatically. Now you saw this. The first thing is topological sort. We did topological sort, and then we did said out dot grad is equal to 1.0, and then we said reverse topo, and it should happen. So if I now draw dot of out, so hopefully I will see the gradients, and you can see the gradients are here. Okay, so gradients go updated. If I just suppose, if I again take that initial node, I'll take forward pass. So I have this thing over, if I can run it. So initially I had this, these are my nodes. Okay, and if I run forward pass, and if I apply sigmoid draw, so you can see the gradients are 0 everywhere. But now I'm not running this cell. This is manual backpropagation, and what I'm running basically is from here. So I'll do topological sort. Okay, out dot grad is one base case, reverse topo, and then draw this. So you can see the gradients are updated. Initially it was 0, now it got updated. Okay, so this is what is done in backpropagation. Now we check the forward pass. We checked forward pass in our case, we checked forward pass with PyTorch, but before doing that, we'll have to somehow add a function. So okay, so how to add this into the main code that we have? So I'll take this build function, and I'll write a function backward. Okay, so when you'll just enter loss dot backward. So how to do that? Go to params class, go back to that class, and then add one more functionality over there. So you have this class, params class. So now what I can do is, I'll say definition backward. Okay, I'm adding one more function, that is this backward. So after this I'm adding self, and the first thing that I have to do, oops, I should not have pressed this enter. Okay, so once I press this, so now what I can do is, the first thing that I have to do is to apply topological sort. I have copied already the topological sort, and this is what I am doing. But in this case, topological sort should be called on self. So whatever node is given, so I have to call that. So now I'll get this topo list. The topo list will be a it will be a graph. It will be a list of nodes which will contain the nodes in topological order. And then after that, I'll reset the gradient. So why should I reset the gradient? Because every time I am updating new, I'll reset the gradient. So how to reset those gradients is like this. So you take, oops. Okay, so if you see this, so what I'm saying is, I'm saying n dot grad is equal to 0. So take all of these nodes from topological list, the list which contains all the nodes in topological order, and put n dot grad is equal to 0 initially, and then with the base case, the seed gradient is this. So self dot grad is equal, because I'm doing it from the last node, then I'm saying self dot grad is 1.0. So this is what I'm doing, initially putting all the gradients to 0, and then I'm saying put the seed gradient or the base case is equal to 1.0. Then I know what I have to do is, I'll just iterate through all of these nodes in topological order, and then I'll say, so if I'm here, so in the backward pass itself, I'll paste this. So if you see for V in reverse topo, so because I have built this list, all the things that I did, I'm just putting them under this function define backward, definition backward. So whatever, if I call now say loss dot backward, so all of these things will happen. Okay, now I'll put the end to this suffering as well. So we will not, so I'll run this. I hope this is working correct. So now what can I do is, I can go to the end, I can delete these lines. So I don't need this. Okay, so I don't need this out.grad. So this was just for showcase. So I'll just remove this as well, because I have now put them under a function. So if you see, so I'll just need this one. I'll need this param, so I'll run it. So if you see, okay, and I'll do forward pass, and I'll apply sigmod onto this. Now if I do draw dot this, so this is my initial state. Okay, now what can I do is I just have to write dot backwards function, and hopefully it works. So I'll have to say out dot backwards, out dot backwards. So if I apply this, so this is basically doing the gradient descent automatically. So if I, hopefully it should be, oh good, it is without errors. It's rarely the case. So if I now press enter, so you can see the gradients go updated. Beautiful. So what I did so far is, whatever pieces we studied about, I stuck them together and I made a function which is called as backward. So now I'm just calling out.backward, and it is doing the whole back propagation that we were doing manually automatically. Okay, any questions so far? I'm so happy that it's working. Now that we saw that we have done back propagation automatically, I'll put all these steps together. I'll delete the code and I'll put all the steps together. So whatever is to be deleted, I delete that. So what are the steps that we'll take? We'll have data initially, we'll do the forward pass, okay, and after that I'll perform back propagation, and then we'll do updations, okay, and then before next step I'll do reset the gradients. Okay, let's do that. Now if you see, internally I also do it here. So internally I'm resetting gradients in every step. So this is my data, so I'll just take it separately. Let's keep it here. This is data, and let's keep this forward pass in one cell. So this is forward pass. So I'll name this. So this is my data initially, and over here this is my forward pass. Forward pass, and then I have having this draw function, and this is my backward pass. This is my backward pass, and then I can have updations. So I can do updates. Okay, and then I'll have to compute loss. This is my updates, and I'll have to compute loss. So right now, if you see, loss right now it is out here, so you can compute that. So this is the loss. So if you see this 0.6225, this is your loss, and you want to decrease it. So how can you do? You have to update. So you'll do forward pass, and then you'll suppose do this backward pass, and you'll check for the updations. I'll write the whole loop, and then I'll compare it with the PyTorch. So what I'm trying to do is, so leave it here, consider this from here. So you have this pass. This is building a neuron. Okay, this is your forward pass, and now this is your backward pass, and this is the gradients which are computed. And till here, this is whatever we have done so far. Okay, so this is your neuron, this is your forward pass, and this is your automatic backward pass, and now you can see these are the gradients. So I'll do the same thing with PyTorch now. And I'll see if the same thing applies. I'll not write this try catch blocks, leave it. Okay, so now if you see, what I have done is tx1, tx2, the same thing that we did. So requires I'm putting gradient everywhere. Okay, so I'm doing this. This is my forward pass till here, and this is torch.backward. So till here, this is done by PyTorch. And now I'll print it, and then I will compare. So if you see over here, suppose w.grad, this is match is true, that basically means it matched. So the custom was 0.47. If you see, the torch also gave 0.47. w2.grad is 0.705, and torch also gave 0.70. Custom gave 2.3 for this b grad. If you see, whatever we computed here, okay, all these gradients, if you can check in the PyTorch, they are the same gradients. So how did we do that with PyTorch? So I already showed you. So this is the result, t1 tw1.grad. For the each tensor, there also is this grad attribute which you can take and just plug the value dot item, and you can see the values. And what I'm writing over here is I'm saying that you have to compare for numerical equality. If let's suppose you subtract these two values, w1 grad dot tw1. So this is my custom implementation, and this is the torch implementation. And if you subtract these two things, and if you get it less than total, because there will be some floating point error, so I'm still keeping this total, and then I'm saying if this matches, and then this is equal to this will be true. So here I am giving that this is true, and you can clearly see over here. So I have W1, W2. These are the three important things: weights and biases. Two weights, W1 and W2, and one bias. So if you see, this is true. Okay, now you can see that clearly. Whatever PyTorch compute and whatever we did by custom implementation, the same thing happened in both the cases. Okay, and then you have to update these parameters, and if you want to update them, you can update them easily. So as I was telling you people over here, so your first step is forward. Your first step is data. So this is your data, and this is your forward pass. And after that, you have your backward pass, and you have to do updation. So how to update the values now? So you'll take each of this and update it. So you have, suppose, these values, okay, and you can update them. You have x1 w1, x2 w2, sum and z. All of these values can be updated. So how can we update them? You can just take the values and update it. So usually we'll update only w1 and w2. That's your one weight and bias. So you can do the updations over here, and then you can check it. So let's suppose w1. How to update now? So whatever gradient you got, so you have this minus equal to. So this is basically initially whatever the value of w1 was there. So you'll take that w1 and you'll say w1 minus, and what you will do is you'll take some learning rate 0.01 suppose, and then we'll multiply it with the gradient. So whatever gradient you computed for this w1 dot grad, okay, and you will do this. You'll take this value and subtract it from here. This is what you will do, and you will do it for all the things. So here why the error is because we have to take data from it. So you have to say w1 dot data. So the data should be decreased, and then 0.01 multiplied by this, and you also have to take care if this operation is valid. If this is not valid, we have to say param. So now you see we updated w1. Okay, similarly we can do it for w2. w2 dot data is equal to this. So this is w2. I'm doing updations with some learning rate and the gradient. So gradient is giving a direction. So let's suppose bias also. We'll just update these three parameters. We can update all the intermediate things as well, but right now we'll just update this minus 0.01. This is the learning rate, and multiplied by b dot grad. So this gradient is giving it the direction. So let's reset it. You can see this is our data. Okay, and after data you have your forward pass. So out basically is telling you how much off are you. Okay, this is giving you that. And after this, you want to, suppose I'm drawing it. You can see initially the gradient is 0.0, and out dot backwards once you perform this. Okay, and if you see, consider this to be loss, this to be your loss. And now once I'm doing updates, so I'm doing updates. So if I do forward pass again now, I'm doing forward pass, and then if I draw this, you can see initially it was 0.6225. Now you saw that it is 0.6147. It got decreased. Okay, again if I do backward pass, compute the gradient, update rule, and once I have updated, again run the forward pass. Okay, then again draw it. It was 6.147. So if you now see, it reduced 6.068. Now loss is going down. If you see, we are navigating that terrain, and that terrain saying us initially we had some value, and slowly we are going down, 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 and you can clearly see. What is the step? First thing is you apply forward pass. Okay, now if you see, I have already applied forward pass. Now I'll apply backward pass. So this is backward pass. Backward pass will give you gradients. So I'm updating the values. So once I'm updating, so what I'm trying to do is I can again print out. So out over here is 0.068. So this was initially, and now after this I can still again run forward pass, running the forward pass, and then you can see if I say now draw out, you can clearly see this is again going down. So forward pass, and then you run backward pass. Okay, then once you run the backward pass, you will update the weights, and you will keep on looping around. So these couple of steps are there, but make sure that you reset the gradient. Why is gradient reset required? Because each iteration you are doing is you don't want to have effect of previous gradients. You want that once you took a step, you will start fresh. You will say that okay, now I am at this point, I want to get the direction. Any questions so far? You can clearly see that the more I run this, and this loss keeps on decreasing because it is going to down to that terrain. And what I was doing, we're having data, applying forward pass, and then applying backward, and then updation, going back, and keeping a check, is loss getting decreased continuously or not. Any questions so far? So the typical things go like this. So I will just remove this code screen for a while. So you see, so we're applying forward pass first. So what does forward pass does? So forward pass basically is prediction. It is making predictions. Whatever you want to do, it is doing that. So it is making predictions. And based on this, you know that the predictions are off, and you have to compute, you use loss function and some things over there. So you'll for in forward pass, after that, suppose you are using loss function. So loss function is basically telling you the gradient. So here after forward pass, you will use, suppose, backward pass. So this is the general step. I'll just keep some space in between. So you'll use backward pass. So backward pass will help you computing the gradients, because you are off by, suppose, backward pass will also involve your loss function, because in backward pass your loss function is involved. So this will tell you how to nudge your values, how to nudge these weights and biases so as to get better predictions. So you will perform backward pass. This will basically give you gradients. So output of the forward pass is predictions. The output of the backward pass is gradients. So it will give you a gradient. So what will you do with those gradients? You will make updations. So updations basically by using gradient descent. Updated values. So whatever the learnable parameters are, these weights and biases, once you use this gradient descent, so what will happen is, so you will take, suppose, this W, and you will say W is equal to W origin, initial W. So this is your final W. Yeah, after some iterations, you will take initial W, and then you will subtract it with some learning rate, multiply by the gradient. I'll just write grad. Okay, so this is what you do. And now you will again perform forward pass. So you'll perform forward pass. Basically, what will forward pass give you? It will give you new predictions now. And now you know that before new prediction, you will be saying, are the predictions good or not? If you still feel, okay, I should keep on doing forward pass. So before this backward pass, within the backward pass, you will reset the gradients. So you will reset the gradients. That's why I left the space. Why are you resetting the gradients at this point now? Because the computational graph that was internally laying out, it might have the gradients from previous pass, or it will have the gradient. So before going to compute new gradients, I actually want to reset the gradient. I want to start fresh, so that the direction, because the gradient is giving me direction, the direction that the gradients are giving me is correct now, is correct as per the updated weights and biases. So forward pass, the output is prediction. So forward pass is actually giving you prediction. So what is backward pass doing? So backward pass is using those predictions and seeing how good it is, and it is using loss function, and then you basically back propagate. You are computing this dou loss divided by with respect to parameters and bias. How can I nudge weights and biases of this so that I can get this loss function as minimum as possible? So how to get this? How to get that? You will perform back propagation. So backward pass will give you gradients, gradient with respect to each of these weights and biases. So what is gradients basically? So gradients will give you direction. So which they'll give you direction of steepest ascent. So you will go steepest descent. So that's why you will use this gradient descent. Again, once you applied those, you will have updated forward pass. You will have updated predictions, and then you will reset gradient, because once you made predictions, now you have you use new weights and biases. So you are thinking that if I used the earlier one, if I use earlier this gradients, so it will not converge nicely. So what I can do is I can reset the gradient so that I'll start fresh. Okay, these are the typical steps: forward pass, reset the gradient, and within the backward pass, and then apply gradient descent, and then again move the forward pass, and this will keep on happening till you reach convergence. What is the meaning of convergence? Convergence basically means where you are satisfied. Okay, my answers are quite good. My answers are almost near what I want. So this is the meaning of convergence. Usually you can do it for hundreds of epochs or howsoever you want to do it. Okay, until you say that okay, my loss is in a range where this is an acceptable range. Okay, yes, I'll take questions here. Now that we saw that what are the different steps, so we started with a forward pass, and then we did backward pass. After that, we applied gradient descent. That is, we updated the weights and biases, and then we again applied forward pass. So the things that you have to remember is forward pass is giving you predictions, okay, and backward pass is giving gradients. So gradient basically means direction. It is giving you some direction, okay, and then you use this direction to nudge your weights and biases, and so that your final loss, the loss function that you want to decrease, so this will be decreased in that way, so that once you have initial weights and you have these gradients, so you can do something to these initial weights, basically subtract this term over here, so that you land at the weights which will help you to decrease the loss. So this is what we have seen so far. Okay, so this is written over here: forward pass, backward pass, gradient descent, and this updation. And we reset the gradients. I think I have given you explanation why do we reset gradients, because each time we want to start fresh gradients. That is, gradient is equal to 0.0. Zero gradient means no direction, as I said. So if you have gradient 0, so you have final is equal to, you take initial weights and you subtract it multiplied by the gradient. If this gradient has some value, it means it will nudge the value, but it has 0 value, that means no direction. It will keep the final and the initial gradient same. So that's why each time you do it, it's important that you reset the gradient. If you don't reset, what will happen? It will take more time in convergence, because it will take wrong steps, so it will take more time in converging. Okay, this is the story so far. Now what we'll do is, we have also compared it with PyTorch. Now we'll first create a neuron from whatever we did. We created actually the things that I've done so far is, we create our custom data structure. We have custom data structure, which is called as parameters basically. So this is what we named it as. Okay, this is what we have done so far. And then by using these params, we created one neuron. And in this params also, we are now having our own backprop method. So that is automatic. I can just write autograd. So we have autograd, that is backward pass. We just write backward. So from this backward, we can do the backpropagation. Now that you have the data structure, but now we'll have to utilize this data structure. So once we utilize this, we'll have to come up with the concept of neuron. And from this neurons, we'll come up with concept of layer of neurons. And from this layer of neuron, we'll come up with multi-layer perceptron. So this is what we have to do. So far, what we have done, we have just laid the groundwork to make this params. So what this params is, it is giving me a node in that huge computational graph. So as I said, one thing that I want to reiterate over here is, so this network, so which we usually make, so this is the visual representation. Visual representation. If you have seen fully connected layers, fully connected networks made on internet, so you would have seen such examples. Okay, and then let's suppose you have two more layers, something of this sort. Okay, these are fully connected. Okay, so these networks are just visual representation of neural networks. This is not, this should not be confused with computational graph. So this is not computational graph. This is not computational graph. Okay, so what I am showing you over here, because you saw that once you were taking an example of one neuron. So one neuron had multiple nodes. So you had x1 as one node, w1 as other node, x2, w2, and bias. All of these were nodes. Okay, so for one neuron, we'll have a computational graph. Similarly, for a whole network, we'll have quite more complex computational graph. But this is just a visual representation. This has nothing to do with the reality, the thing that's happening underneath. So what have we done so far then? So we have just made a custom data structure which we call params, and a param supports different operations, and it also supports now backward pass. You can just say suppose out dot backward, so it will perform the whole back propagation on its own. Now we are at this step. We want to create a neuron first. Okay, after this neuron, we want to create layers of neurons, and then we want to create multi-layer perceptron. So this is left. So till here we have laid the foundation. Now we'll go to this step. We'll create neurons. Okay, let me show you the code window. Now I'll go to defining a neuron, because we have params and we might also require to define more things, and we'll keep on adding the functionalities to this params class. So params class is here. So if you see, this is our params class. So we have so far these operations, and we have different functions that we support in this, and we will have to accordingly keep on extending the functionality as per our requirements. So now we'll go to single neuron. I'll just copy paste and explain the code so that I don't make the errors while typing. So let's implement a single neuron. So I'll start it from here, and then I'll see if I have to extend the functionality of params, and we'll extend it accordingly. And as I told you, extension can be done at different level of abstraction. You can sometimes, as I showed in exponentiation, you can directly use exponentiation, or you can implement your own exponentiation method. So now the first thing is, I'll import random module, because I might have to randomly initialize these weights and biases. So this is the first thing. Now I'll define a class neuron. So in that neuron, it should be given some input, because you know that neuron will take some input, and then based on that, it will adjust it'll have its weights and biases. So let's call that class neuron. So if I write here class neuron, and then in this, so I'll initialize the method, and I have two things. I'll have weights and biases. So what will neuron take? So if you see the neuron, so neuron will have how many inputs does it take, those w1s and w2s, w3s, and those will be our weights for that neuron, and then it will have x1. So if you see over here, so I'm saying init, and this is an input, a number of inputs it's taking. So based on these inputs, if you see, I have to create those number of weights. So I am writing over here, this is a for loop. I'm saying for this dash in range of this, so I want these many number of random weights. So I'm initializing self.w. So let's suppose if this neuron is, say, having in our case x1, x2, w1, w2, so here I'll have this 2 input, and an input will be 2. So based on this, I'll create 2 weights, w1 and w2, and now bias always will be equal to 1. So that's why I'm keeping it self.b is equal to params, because it should be of type params, and random.uniform is I want to have a random uniform random number which should be kept as bias. I think these two lines are pretty clear. And then I'll write one more thing over here. So I'll write def call. This is what internally happens in Python. So this def call, actually when you write in a certain way, so I'll just say print So to say how this call does is, I will first show you the functionality and then we'll add its functions. Let's suppose print hi, something of this sort, which I generally do. Okay, so is there some issue is there? There's the problem with copy and pasting, so I'm just indenting. So what should you do now? So let's suppose if you are calling this neuron, so call, let's suppose we'll take two input, we'll take suppose 2.0 and 3.0, something of this sort. I'm saying x is equal, I list 2.0 and 3.0. So let's suppose I will give it as an input. So if you say n of, so n is equal, so I'm calling it neuron and neuron of 2, suppose. So what will happen because of this neuron of 2? So this neuron of 2, so this will initialize this, so it'll have two inputs, so w1 and w2, and a bias automatically. Okay, so when I create this, so if I say n of x, so n of x will automatically call this. So when I will write it in this syntax, n of x, so this will call this. Okay, that's what this render method does. So if I run this, so you can see it showed hi. Okay, when I say n of x, so this is what will be called internally, this def of call. So in this now I have to perform the calculation. So what I should do is I should perform aggregation and the activation. So how to perform aggregation is, so I'll say first zip of this, because I have input x and w. I'll have x1 w1, x2 w2. So in Python there is a good way of doing it. So I'll zip this x and w. So in this, if you see, I'll zip this x and w, so that I have two iterators, one going through x and another going through w. So I'll say xi comma wi is now it's going through this. So now I'm zipping this. So now what should I do is I'll add these two, I'll multiply these two things together. So I'm saying xi multiplied by wi, okay, for xi comma wi in zip of this, okay, and then I have to sum these things up. Okay, this is sum of these things. Okay, and this I can call aggregation. I hope this is clear for everyone. So you people have seen enough Python to understand this. So let's suppose I can call this affine transformation or something. And now I also have to apply activation. So keeping this simple right now, so later on you can change the functionality. I can use tan h. So I'll say tan h of this. So let's suppose call this pre-activation or ACT. So this will go input to the activation. So I'll say out is called act.tan h, and I'll have to define tan h. So here, so I'm saying activation is equal to act.tan h and return this out. Okay, I'm just copying and pasting it, return this out. So if I do this right now, I suppose there should be some error, because the thing is we haven't defined tan h. I hope so. Yes, there is an error because we are saying unsupported operand multiply this. So there are a lot of errors. And the first thing I can clearly see is one error is that this tan h is not defined. So we'll have to define tan h. Let's go to our parameters class and we'll define these extended methods. Okay, and we'll also have to define its in backpropagation we'll have to define its derivative as well. So here we'll define tan h. So if you see tan h, so I can directly use it, or depends on you what is the level of abstraction you want. So in this case I'll just copy and paste this tan h function over here. So mat.tan h is a function directly which you can use, or you can directly go to definitions. So in here I will paste it over here. Okay, so if you see this, so this is I'm just using mat.tan h over here, but this is one of the ways. What you can do is you can again abstract it out. You know the definition of tan h. So that is some e to the power something minus e to the power something divided by something. So there is a function which you can directly take and you can code that up instead of this tan h. So it depends on you what is the level of abstraction that you want. So now the other thing is that I want is now I have to also define its derivative in gradient in our backpropagation. Okay, so let me put that also. Okay, let me copy and paste directly. So what you can do is, so take this and instead of this else, I'll just remove this. I'll again write lf. Okay, I hope this is the derivative of tan. This is how you do it. 1 minus s multiplied by s. Okay, this is the derivative of tan h, this one. Okay, so far good. So what I have done is I extended one more method, that is tan h. And after tan h, what I did is I also added that into this backpropagation method, that is the backward pass. So I'll again run it and see if there are more things that are to be implemented in order to support this. So we are here. So but we had some other errors over here. So which I told you that we have to implement some other operations. The first thing what we'll do is we will also see that if the operation is not paired. So in the basic operation, if you see, you have this self and you have this other. Sometimes what we can do is we can say a plus 1 if this a is a param and we have 1 is not param. So that I was showing you over here. So say we have this a and I have this b. If I say a multiplied 1.0 multiplied by a, 1.0 is a float value and a is of params class. If I try to do something on them, you can see that it shows unsupported operand. Float and params, you cannot do this. Okay, and then what I have to do is I can say take this 1.0 if self or other, if one of them is not say of params class, so I have to convert that into params class so that the operation is compatible. So in this params class, so what we can do is, if you see this method, if you see this add, multiplication, these methods, suppose you see this dunder methods, so we'll check for this. If the instance, if self or other is not of type say params, convert that into param. So I'll just copy and paste the code over here so that you can see. So self usually is of params class and then we have to check it for other. So for this add, what we can do is I'll just paste a line. So what will this line do? Okay, so if you see if not instance other params, that means it is checking. So this line is checking that if other parameter, the other that you are giving, we did say a plus 1.0, a was of params class, 1.0 was of not params class. So it will check if the other is of params class. If it is of params class, then it will do nothing. It will directly move on to this. It will say out.params and it will add the data and do everything that is expected out of it. But if it is not of the params class, so it will make it as params class. Say if not is instance other param, so what it will do, it will take this other and it will wrap it around that params class. So that's what it will do. Similar thing for the other, similar thing for this multiplication. Similar for multiplication, if I just copy and paste this. So you can see same thing I am doing it over here for addition and multiplication. So now the problem won't be the problem will still be suppose that if I do a plus 1, this will work, but if I do say I'll just run this cell and now over here, let me do that over here so that, so if I paste this line over here, I am saying a dot param. So if I say suppose a plus 1.0, so you can see that this is working. A plus 1.0 is working. But if I say 1.0 plus a, because now the self over here, the first argument itself is not of params class, so it should throw an error. Hopefully it will throw an error. You can see it's throwing an error. It is saying unsupported operation, float and params, I cannot add them together. Why? Because the first thing, the self itself is not of params, so it has to convert it. And for this we have special dunder methods which are called R multiplication, right side multiplication, right side division or something of that, which is called R mul, R add. So what it will do is it will first check if 1 plus, because these operations, if you know, they are symmetric operations. That's 1 plus 2 is equal to 2 plus 1. So I can just reverse the places. So I can use the R mul. So let me just copy paste the R mul code. I'll show you what it does. Just let me copy it. So I'll add a couple of functionalities over here. Okay, this is our class where we want to add this functionality. So this after negation, I'll add this. So if you see, I have added two functionalities. One is R add. R add basically means it will reverse the operation. If you are doing a plus 1.0, that is possible. But if you are doing 1 plus a, that is not possible. So it will go over here. It will change the operations. It will make self to other and other to self. That's what it will do. So if I now run this, say if I will run this, and I'll perform this operation. Now if you can see, this is possible now. So two things I did so far. The first thing is that if I add a floating point to params, I will check if the instance, other instance is of params class, and if it is not, I'll wrap it around the params class to support this operation a plus 1.0. But now also, because these operations are symmetric, 1.0 plus a should also be possible. So for that I have added one more functionality over here, that is this R mul and R addition. Okay, so these are here. If you can see, this is R addition. What it does is self and other. So basically it reverses the order of these operands. Okay, a plus is a symmetric operation and multiplication is also a symmetric operation. So I can add R addition and R multiplication here so as to support this thing. So this is what we did so far. So if I now run this class, and now I will be able to run this neuron, because in this neuron we're doing this. Okay, so now you know how this neuron was constructed, and if I run this, you can clearly see it is running now. Okay, this params classes. I just want to show you how a neuron looks like, so that I'll give a better explanation over here so that you understand it from the code perspective as well. If you have questions, please let me know. So what will happen over here, you see the input over here is self and input. That means number of input it will take, and you know neuron can take any number of inputs because it is not just the class where you just give one input. You can give multiple inputs. That's why I'm taking this n input. So if this n input is suppose 4, so you'll have x1, x2, x3 and x4, and corresponding to each of this, you know, you will have weights, weight 1, weight 2, weight 3 and weight 4, and you know it will have a bias towards it, and after that it will have an activation. So now if you see this line over here, this line is saying self.w. So but you know that these w should be equal to number of inputs. Okay, so that's what I'm doing over here. So this loop, if you see this loop for dash in range, a number of inputs, so I'm having these many number of weights. Okay, number of weights is equal to number of inputs, and this is for a single neuron, and then I'm adding one bias. Okay, and I'm uniformly at random, I'm just taking from -1 to 1 range. And then if you can see over here, then I'm calling it. So I have already explained this. So this xi, wi are two iterators that are going through this x and xw, and that we are multiplying them together, and then we're adding these things up. All of these things are adding xi, wi plus x. So this is summation of this over here, if you see, is summation of xi, wi plus bias, and this I goes from 1 to number of input nin. Okay, that's what this line does, and then we are applying activation onto this. Okay, that's what this neuron does. So this is a tan H activated neuron. I hope this is clear. Now from this onwards, we'll have to go to a layer. If we now know that how this neuron works, we'll also code a layer. So let me do that. I'll just delete this line. Okay, so what I can do is I can now create a layer from the neurons, because I know how. The first thing is you should have abstraction. You know how a layer looks like. Now you have a neuron, you have to put them together. So for that, we will define a layer, and in that we will define class layer. Let me do that. So I'll have class layer. So class layer is there, and after that I'll have my initialization method. In the initialization method, I'll have number of neurons, because now I know each layer should contain neuron, and neuron I have already defined, and I can call that. I can use that call. So I can say def initialization. So if you see this self dot neurons, so I'm taking number of neurons, how many of you want. So you want input of the neuron. Each neuron should have an input, number of input that you earlier saw. Neuron has number of inputs, and then it has one output. Okay, so but you know the number of neurons. This n out over here, this is the number of neurons you want in that layer. This n input is the input that you want each neuron to have. That's what we are doing over here. So you are having this loop for underscore in the range of n out, that is how many number of neurons you want, and what is the input that each neuron should have. Okay, this is each neuron's input, and this is how many number of neurons do you want. And you have self.neurons, you are creating a list of such neurons. Like you have a list of neurons, this is one layer basically, this is a layer of neurons now. A list of neurons is a layer of neurons. Okay, now we have to also call this. So how do we do that? We'll do the forward pass for all the neurons together. So we'll again have this definition of call. We'll define a functionality. That's this. So def call self comma x. So this x will be taken as an input. Okay, once this is taken as an input, now you can perform forward pass on x for each neuron. For each neuron, the computation will happen. But how many times you have to do it? You have to do it for all the neuron in the layer. Okay, the thing that you perform, the calculation that you perform for one neuron over here, you have to do it for all the neurons. That's why if you see in this case, so you are saying that for n in self.neurons, because neuron, we have a list of neurons now. You have list of neurons, that is in the layer, you have this list of neurons. You'll take each neuron and perform the forward computation of each neuron. And this n of x, this will call this. This is calling this neuron call. So it is doing the computation for each neuron. And then it is saving it as a list. So okay, if you have say n number of neurons, it will store as it as a list in outs, but it's a single neuron. Now it will give outs of 0. I wouldn't want list, we just want the output. And if length is equal to 1, that's what we are doing. Otherwise, you give the whole output to me. Okay, I'll again show it visually to you people. So we have layer of neurons like this now. So you have, let's suppose 3 neurons, 1, 2 and 3. So in this case, this n input we want, and output is already 3, because I have defined that I'll have 3 neurons. Suppose each neuron now takes 2 inputs, 1, 2, 1, 2, 1, 2, something of this order. So this will be 2, 3 over here. This is what will be formed, and you will have one output over here. So what will this line do is, so this line will take all these neurons. So these neurons will be initialized in this self.neurons. We'll have 3 neurons in this, and it will have their own weights and biases. And now once you say this, once you say outs is equal to n of x for all of this, so it will take each of the neurons. So you see this for loop over here, it will iterate through all of these neurons that are in the list. And once it is there, and then it will call this n of x, it will do the forward pass that we have defined in the neuron. So it will do that weights and bias, summation of w and xi plus bias for each of the neuron, and it will give outputs. It will give 3 outputs in this case. Now if you see, this outs will be a list. say the value is 0.4, 0.6 and 0.8, something of this sort. Okay, so that is what will be outputted over here when you call this, when you say layer of X. So this is how it will be evaluated. Okay, now if it is a single neuron, say we are not defining, we're just defining a single neuron in the layer, that time we don't want this list, we just want one value. That's why I have written over return out store 0, return single value if it is just one neuron, because it will always form a list. So for that list, just give me the first value that's in the list, because there is only one value. Otherwise, if it is not the single neuron, if it is multiple values, then give me whole of the list with me. Give me whole of the list. So I'm giving this outs with me. This is how a layer is working. I hope this is also clear. Now we have a neuron, we have a layer, how it works. Okay, we'll also check if there is an issue with the layer. So I hope layer should work. So over here you can see layer is working. So this I'll also delete, because we also want to create new MLP. So if I run this, you can see this is the layer. So this is a layer of like input will be 2, okay, and this is the layer of 2, 3 that I showed over here in the diagram. So this is what it is taking. It's taking 2, 3 over here, 2, 3 over here. It is repeating the input everywhere in all the neurons. And then you have 3 neurons and it will give some value. Okay, so what is the value over here? If you see, this is 0.9. I wrote 0.4. I can just adjust the values according to what we got over here. 0.93, and this is 0.99, and this is 0.90. These are the values that we have over here. This is what we got as an output when we performed this for a single layer. Now we need to make multi-layer perceptron. So in the multi-layer perceptron, the only thing is I have to now stack the layers together. Initially I had a single neuron. From the single neuron, I concatenate the neurons. I had a layer of neurons. Then I need to have multiple layers. Okay, that's what I want to do. So for that, I again define a class MLP. So class MLP is over here. So this is class multi-layer perceptrons. Okay, and from this, I will define initially inputs and outputs. So I'll show you what inputs and outputs are. So if you see over here, I have said this is an in and this is an out. So an outs will be a list. So you'll have an input and then you'll have a list of outputs. So it will be something of this sort. Say if we have an in and an out over here, it will be, say we have input 3. So suppose the vector that we have, the data that we have has 3 features. So we'll have 3 features. Then this and outs will be a list. So list will tell me in each layer how many neurons do you want. Suppose I want neurons 4, 4, 1, something of this. So what does this mean is, so this is, we have 4 layers. Initially you have again 4 layers, and at the end you have 1 layer. So this is how it will make, and each of this will take 3 inputs. Okay, this will take initially 3 inputs. Okay, and then this is fully connected. This will again go after this. So this will be connected. All of these will be connected. So, and you know how to make a neural network of that sort. So now you have this 3. You have 4, 4, 1. This is I'll concatenate both of the things together. So if you see over here, so I am saying SD is equal to append this list together. So you will get a list, and then you see I'm saying for I in range of length of n outputs. So I'm saying what is the length of this? So how many layers do you want? So the length of this is the number of layers. So the length of this n outs is the number of layers. So in this case we want 3 layers. So 1, 2 and 3. But in each layer now you have 4, 4 and 1. In the first layer, suppose we want to have 4 neurons. The second layer you want to have 4 neurons. In the last layer you want to have 1 neuron. Suppose something of this sort. So we'll iterate over this. So what we'll do is we'll start from here. So we'll concatenate these 2 lists together. So the list that will be formed is like this. So you'll have 3, 4, 4, 1. Okay, so this is our SZ. So in this case you have this SZ over here. So I have input, number of inputs that will be going inside the network, and then I have this and outs will be the layers, and each layer will contain certain number of neurons. So you have 4, first layer will contain 4 neurons, second layer 4 neurons, and third layer 1 neuron. So what I'll do is I'll iterate, I'll make like this because I want to create a layer. So for layer, you know, we have to have an input and an output. So what I'll do is I'll say for I in range of lengths of out. So give me 3 layers. So basically this is number of layers. So for each layer, so I'm creating the number of layers. So what I should do is I should create a layer. So how should I create a layer? The first layer will be this. So input will be this and output will be this. Second layer will be this, and third layer will be this. That's what I'm doing over this in this case. So I'm having a network in which I have certain layers now, which are placed like this in the neural network. We place first network, then second layer, then third layer. So what I want is I want to create a network out of that. I have defined neuron, I have defined a layer. So I am taking the input number of what is the input, and input means number of inputs for the first layer, and then and outs basically means, so this will be after the layers, what would be after the input layer, and we have to define that in an outs. The length of this, so n in 4, 4, 4 is an outs. So this length of this will be saying number of layers. So you should remember this. This is how we have created this multi-layer perceptron. So if you understand this, so now we'll also have to define call for this, and call is pretty easy because we'll use the other methods. We'll call layer, and layer will itself call neuron. Okay, so that's how it will happen. So give me a second, I will just paste that line over here. So call. So what will call do? If you see, the call is there for each of the layers. So now you have defined these layers. You have this layers now. So this is a list of layers. Okay, and it will say for layers in self.layers, take all these layers and then x is equal x dot layer. Perform the forward pass for each layer. But this layer of x, you know, will call this. It will call this, and in turn it will call a neuron. Okay, that's how it will do. That's why we created a params class first, and then neuron, then layer of neurons, and that's where we got this multi-layer perceptrons. Now if I just call this, so you can see this is how it looks like. So I am having, suppose, an input which takes 3 inputs. So 3 inputs, and the first layer will have 4 neurons, second layer 4 neurons, and third layer will have 1 neuron. You should be able to visualize this. But I said there's a huge difference. The things that I show here is a visual representation, but what is happening underlying is a computational graph. So if I just run this and perform this draw.x, you can see over here, this is what is the computational graph like. And I am applying 10x, and this is a huge computational graph. Do not confuse it with the visualization, please. You should not confuse, keep that in mind. So whatever visualizations you have seen so far, they are just visualizations, they are not the network. So this is the actual computational graph that we have made. This is quite complex and quite hard to visualize if we don't have these sort of things over here. So I'll take a pause here. I'll take your questions if you people have. The picture that you should have in your head so far is that once we want to create something, so we had something in the head that this is what we want. Suppose we want to train a neural network. So for that, there was no data structure in Python. So I couldn't use directly lists or something of that. So I had to create a custom data structure. So once I did that, say I created some custom data structure, which was called as params. Now it needed some methods, it needed some variables to hold data and some other things. That's what I did. So I made a custom data type, which was called as params. So let's suppose this is params. This params is my custom data structure. Okay, why do I need that? Because I didn't have, in Python, we had nothing like this, because we needed data where we can have data. Okay, we needed its gradient. Okay, with respect to the loss function, we needed its name also. Suppose the name was given was something else, suppose label, and we needed what operation was there. So we need all of these things, and there was nothing like that in Python, or there is nothing like this in the language. So this is a real world problem. So the first thing is you have to create this class on your own. You have to create this custom data structure. That's why we learned about class and object. So we are creating this. So from this, now we initially performed the manual backpropagation. So we had to have some method which will perform this autograd automatically. Its name is autograd. So autograd basically means it should perform the backpropagation automatically. On this, we gave some functionality to this. This was the data structure that holds that thing, and after that we had some important functions. So we had some operations, and the most important functions was this backward. This backward was the function which was performing the backward pass, and we read it in theory and we saw how to implement this. Now we have the whole data structure with us. What is the data structure then? Data structure is basically something which has data and there are some operations defined on it. So we had defined addition. This backward is also now an operation. So that's why it's data structure needed. So clear on till this point. And after this, now we had this building block. So building block was this params class, and we now have to come with a neuron. So that's what we did. So after this, we came up with a neuron. Okay, and we defined how a neuron is. So we use this params class, and we said, okay, it will take some inputs, it will aggregate, it will perform activation, and this is how a neuron looks like. And from the neurons, we created layer of neurons. Okay, from this, we created layer of neurons. Layer of neurons. Now we have to just put these things together. So once we have this layer of neurons, after this, we did what is called as multi-layer perceptrons. This is what we wanted. So we created layers of these neurons. Now we had a single layer of neuron, and we now have multiple layers of these neurons. Put like first layer is this, and then second layer is connected to the first layer, and third layer is connected to the second layer, and then we call that as multi-layer perceptron. We had read each of the theory in the previous classes, and this is where we implement this. This is the story so far. Now we have to use these multi-layer perceptrons to train something. The question that we were initially solving is XOR function was not able. We were not able to use the single neuron, those binary neurons, to map XOR function. Okay, now we know that if we have multiple neurons or a layer of neurons, you can easily map this. You can easily have this XOR function that can be solved by this multi-layer perceptron. We'll start by that problem. Now that we have built each of these nuts and bolts, and we have a multi-layer perceptron with us, we can just define maybe a layer or so. You can define one layer or multiple layers of neuron, maybe just 4 for one layers. We have 3 layers, each of neuron 4, and last layer will have neuron one number of neurons. So we can use this XOR. We know how to create XOR data. Okay, for this, the data of the XOR function was something of this sort. So XOR had this data. So you had 0, 0, 0 1 1 0 1 1. So this was our x, and what was the y? So y is basically the target. So in this case we had 0 1 1 0. So this was our target. So this is our input and this is our target. And we saw that many of these perceptrons, they were not able to map this, but can now this multi-layer perceptron do it? So we'll start with this problem. So we'll start with solving this XOR problem, because we have posed the problem in theory and we built the whole network. This is like thinking like Newton, like if the thing is not in existence, let's create it. Okay, so we created something like a mini PyTorch, and now we'll use this thing. Hopefully it works, hopefully nothing breaks, and we'll use it to map this XOR. So we'll see that what we have studied in theory, so is it actually used somewhere in practice, and is it actually done in practice the way we studied it? And that's the one case. And secondly, will it work? The first question actually should be, will it work? Whatever we have studied in theory, does it actually work? And second thing is, will it work like the way we have been taught in theory? Let's go there now. We'll take the example. I'll again go to the code window. Please ask me as many questions as possible, because if you ask questions, maybe I'll also give the information which was not intended to be given if you didn't ask that question. Okay, let's now define. The first thing is, we'll define the data of XOR. So how can we define? Pretty easy. We know that I have shown you already. So you see this XS. So use param 0 0 0 1 1 0 1 1, and then we have X and Y's. That's what I taught you right now. Let me just close this one. If you see over here, so this is my data. Okay, this is XS and Y. These are my input features, and these are my labels, and this is an XOR gate. Okay, what I want to do is, I want to create a model for this. Let's suppose I'll create the model, say 441, and now if I see MLP, it will take 2 inputs, and I'll have first layer with 4 inputs, 4 neurons, second layer with 4 neurons, and the last layer with 1 neuron, because I need XOR operation. I need 1 or 0, something of this sort, and I want to see, can it map? So I'll create a model. Okay, so how to create that model? I'll leave it as model. So I'll say, so my model is equal. Now I can use MLP. So I'll say MLP multi-layer perceptron, and now what it does take? It's taking number of inputs, that's 2, and a list of basically number of neurons, the number of layers that we want. We want 4, 4, 1. 4 neurons in the first layer, 4 neurons in the second layer, and then 1 neuron in the last layer. Okay, I hope you're understanding so far. So this is my model. So what I'll do is, now I'll have to perform predictions. Okay, once this model is initialized, you know this is my model, and it will have weights and biases as parameters. Let me also show those. Okay, we'll extend one more functionality, because right now I cannot access parameters. Let me clean this. This is a little bit bigger. Okay, I have cleaned this. So what I can show you over here is, I have to get access to these parameters. So let me start it with neuron. So for a neuron, we'll add one more functionality, that is parameters, because we have parameters, the weights and biases, but we have not access for these. So what I can do is, I'll start with a neuron, and I'll take parameters of the neuron. I'll define one more function, that is this neuron, and it should give me a list of parameters. So for this, what I can do is, I can add one more functionality, that is definition parameter self. So when somebody calls parameters, so it will return self.w plus self.bias. So it will concatenate these two lists together, and it will give me a list of parameters. So suppose if I now call on this, so you have this n is a neuron. So in this, if I say n dot parameters, okay, if I call this function over here, so you see these are my params. So this is a list of parameters. So I am now getting these parameters as an output, because I want to have a hold of these parameters if I want to nudge the values of this. Okay, these are my parameters. I can go to each parameter, and I can change data out of this. I can say what is the gradient for each parameter. So I'm adding one more functionality for this neuron, that is parameter. Same thing can be done for the layer. Similar, I can for each layer, I'll extract the parameters. Now let's go to layer, and we have defined list of neurons for each layer, and for these list of neurons, we'll call this parameters class again. So here I'll extend the functionality, that is this. So I'll say definition parameter. So if you see over here, for p in neurons dot parameter, so for each neuron there are parameters. Okay, so I know that this contains a list of neurons. Okay, this contains a list of neurons, and each neuron will have parameters. So I am saying for p in neurons dot parameters. Okay, so I am doing this. I am saying for p in neurons or self dot neurons. So take this. So you have two classes over here. You have the self dot neurons, and within the neurons you have the weights and biases. So it is taking all the layer. You have this layer over here which contains the neurons. So I am saying neurons for p in this neurons, and self dot neurons take this p for each. So it will take for each, it will first take the whole layer. Suppose in whole layer it will take each neuron, and it will call this parameters class on that neuron. I hope this is clear. And now for this multi-layer perceptron, the same thing will be done. Now you have multiple layers, and you will call this parameters function on that. Okay, so here if you see, for p for layer and self dot layer, so we have self dot layers which contains multiple layers. Okay, and each layer will have some number of neurons. So we are saying that for p in layer.parameter. Okay, and internally you know that this layer.parameter will call layer.neuron, so it'll call neuron.parameters, and okay, we'll get number of parameters. This is for MLP, all the parameters for MLP, and this is all the parameters for a layer, and this is all the parameters for a neuron. So these calls are rather like the first one will call the second, and second will call the third one, by that I mean neuron. So MLP will call layer will call neuron parameter. So that's what we are doing over here. Okay, so basically the base call is neuron. I hope this is clear so far. So we have just added one more functionality to these classes, that is the number of parameters, because we need to get hang of those parameters. We need to take out those parameters and do something with those parameters. That's what I am doing over here. So you have this model, and now model contains the first thing is we have input is XOR, and now I have defined model contains number of input is 2. The input actually goes into the neurons, and each neuron takes this 2 input, and the first layer is of 4 neurons, second layer 4 neurons, and the last layer is of 1 neuron. That's how my MLP looks like. So now I can call the parameters function on this. I can easily see how number of parameters over here. Okay, let me do that. So if you see, I can call model.parameters. Okay, I can show you the parameters in the model. So MLP have no attribute parameter, is it? I have not. I should run this also. So this is neurons, run it for a layer. Okay, so this is over here. So now you see, if you see, this is this. I can also call length of this. I can see how many parameters do I have. Okay, length of this whole list. So if I call length of this list, you can see there are 37 number of parameters. There's 37 weights and biases are there over here. Okay, this is my parameter. And if I don't want to have length, I just actually want to have the parameters that I have with me. So these are the parameters I'll have. So each parameter has some data. Okay, and you can make this, you can lay out this network, and you can count the number of parameters that we have. We have these weights and biases. We have 4 neurons in the first layer, 4 neurons in the second layer, and last layer has 1 neuron, because we want 1 input, 1 output. This is what we have done so far. This is the story so far. I'll now remove this model.params. Now we have trained the model. So how to train the model? Okay, so the first thing is we'll make predictions. How can we make predictions? I'll just make one prediction. So I'll show you how to make a prediction. It's pretty easy. We have to do forward pass. Forward pass is prediction. So this is my forward pass over here. So this is forward pass. So what does this forward pass does? So it is taking this x. So we have for x in xs, we are taking this each x. Okay, and we are taking this x. So let's suppose take this x. This is my first data point. Take each of this x from this xs. So after that, pass it to the model. Okay, pass it to the model of x. You know what it'll do? It'll pass through all those neurons, and it'll give me, and it will print y prediction, and we'll see whatever it predict. Okay, so this y prediction will be a list. Okay, we should get output as 4 numbers. So if you see, oh, I just want the data. I don't want everything. I'll say dot data, because this is the whole. This is giving me whole params class. For that, I just want data. Oops, I have to call data. So was it no, this is list. So I should say, suppose y prediction. So if you see this, I just want this params of this. I want for each of this I want data. So I can call this like 0 dot data. I just want to show you one of this. Okay, so this is one. Okay, for this I can do it for all the things, but I'm just showing you one output. For the first, if you see, it is showing answer as 0.69. If I say second value is this 0.53. For the third value, this is minus this. So right now you can see it is random. Okay, I have shown you all of these. So if I just print whole of this y prediction, so it is 4 predictions there, and just focus on this data. I don't want to end the loop to just get out of this, get this out, but I just want you, this is the output. So these 4 things over here are the output: 0.77, 0.58, 0.7, and when I run it again, you will see the values changing, because we are randomly initializing it. Okay, sometimes minus, sometimes positive, sometimes all are positive, sometimes all are negative. Why is it happening? Because we are randomly initializing the model parameters. The neuron is getting randomly initialized, and because the weights and biases are for the neuron, that is taken to the layer, and that's taken to the multi-layer preserver. This is how prediction is made. Prediction is made in the forward pass. And now what we have to do is, so once we get this prediction, so what should we do is, we will then compute loss. So how is loss computed? You have we have studied loss function. So we'll use here MSE loss. So what MSE loss is, take the actual value, because we have ground truth. So ground truth is over here. This ys is the ground truth. This is the actual thing that should happen there. So instead of this 0.2, it should have been 0. Instead of this 0.13, it should have been 1. Instead of this, it should have been 1. Instead of 0.69, it should have been 0. So this is what we wanted. Now we'll have to calculate loss. Okay, so I'll calculate loss over here. So how to calculate loss? So loss will be equal to So whatever we have predicted, suppose we have this y predicted. Okay, so what I can say is I can zip these two things together. I'll perform this. Oops. So if you see this, so I'm saying zip these y predicted and ys together, because ys and y predicted are there. There are these things, and I'm iterating over y predicted over all of this params class. You can see we have a list of params, and ys is the ground truth. Okay, these are also params. So we have two iterators, this y hat and y true. Y hat basically means the prediction, and y true means the ground truth. So we are subtracting them together and squaring them up. This is mean square. Okay, and I am saying mean square over here, and then I'm summing them all of these things together. If you can see over here till here, I am summing these things up. So this is mean square error, and I'm taking the mean. So mean is by averaging it out. So initially I took the sum and then average it out. This is how my loss is defined. Okay, and this we have read in theory. So I am taking two iterators, y hat and y true. So what are they doing is they are going through y prediction and ys. They are subtracting them and squaring them up, and I have to compute loss. But I am expecting an error here because probably we have not defined this division function. We have to define one division function. Okay, so we have to define power function because this power is not defined, and we have to define this division function as well. Okay, so how to do? Go back to params class. Whenever you are doing something of this sort, go back to params class and define these things. As I told you, I have given you the blueprint now, so you can extend this blueprint. Suppose it's like making a building. If you are married now, you have more kids, extend the building. Same thing over here. So here now you can see this params class. We will go back to that because params class is our class that is the building block. So in this building block, we do not have division, we do not have exponentiation. Okay, we can just have two things. Maybe I have defined it in my code. So let me have that. Let me have two more operations. One for division. Okay, and I'll do the same thing for this. Like division, I'll have R division also. Okay, and then I'll have power also. So I'll have over here after multiplication. So I'm adding before 10h. So if you can see over here, so what I did, this is my true division, self divided by other, and I am also checking if other is not instance of param, make it param. Okay, and then R division, you know, I also have to, if somebody says 1.0 divided by params class and or 0 or maybe params class divided by some float or integer, it should happen that. So that's why I have written this R true division. Okay, this true division is what is happening underneath the hood when you perform the division, because we have float division as well. That's why this is called true division, and the other division is called float division when you put that double slash. This is what is internally called. This is the dunder method. And now we also should have a power method. Okay, for power, as I told you, you can it depends on you what is the level of abstraction that you want. So I can add one more thing over here, that is this power. So power method, if you see, I'm again checking the same thing. If self.other, if they are not a params class, so change it. If instances of other is maybe of int or float, and we can say not implement only supports int slash float powers. Okay, and then I'm saying convert this return out of this is equal and return this out. I can say return this out. Return out. Okay, so this is what is done so far. So here I am checking if the power, if the other, the thing that is raised to power, suppose we have raised a to the power b should be of type integer or float. Okay, that's what I have to do, and I am using this self.data multiplied, this is power in Python, and this is other. Okay, and I'm raising an error not implemented if it is other than something. If it is taking suppose complex number, something is given, so it should say not implemented. This is what we have to, and now the problem is we have to also extend this in the backwards class. Okay, now go to backwards class. This is what you have to do. Anything that you do, you have to keep on adding those into backwards functionality. Okay, in terms of division, you have read the nth calculus to do it for powers. If you have something x to the power n, you can easily do it, and nx n minus 1. If it is for suppose u divided by v, you know the formulation for that as well. Okay, you have to just add these two things. Let me add these two methods. I think I have coded them up. I'll just explain them. They're not difficult, you can find anywhere, but you should reason before pasting code. That's why I'm strongly suggesting you not to paste code. You people should reason about the code. So what I'm saying is, if your operation is this, okay, and you know the gradient of this, so this is what should be done, and this is the derivative. Okay, e to the power suppose some x, and this is what should be done. Okay, child take the data and take the exponent minus 1. This is not e exponent, this is actual exponent, x to the power n. That's what should be done. Okay, this is n. Suppose you have some x to the power n, you write n into x n minus 1. So this is at n, and this is the data x, and this is n minus 1. This is how derivative is computed. And you know for division, this is your whole formulation, u by v. Okay, This is a divided by b, and you can compute this by using this formulation. And you know this has been done in calculus. Okay, I'm just converting this into code. If you have questions over here, I think you shouldn't have questions because it's pretty easy. I'm just taking this out. I'm just taking the value out of here. And why am I doing this? Because I have to check that if there are double star in the operation, if somebody has raised something to the power. Okay, and then this division is there. Okay, now parameters classes complete, at least for this case. I'm again running neuron, running layer. Okay, multi-layer perceptron. And now if you see, I'm again having data. So this is now model, and I will make predictions. Okay, this will keep on changing because I am again initializing the network. So if you see, this is changing. Now I think loss should work. Okay, it's working. Beautiful. Now if I print loss, the loss is 1.8. What I want loss to decrease. I want my loss to go down. So how should I go? How will my loss go down? Because if you see, I have this whole computational graph with me now. Okay, loss is also a part of computation. If I say draw dot, and I'll say loss, so there is a computational graph underneath. So if you see this, there's a huge graph which is very complex, and I don't want it to, I don't want people to visualize it, because we have understood it for a couple of examples. That is good enough. And now this loss, if I have it, so I'll backward pass through it. Okay, so I'll say loss dot backward. The beauty of our function is that we can just write loss dot backwards. So if I perform this, so what will happen? Loss will go there. So if you see, loss dot backward, it did the whole back propagation in one go. So once it did that, so now I have gradients for all of these things. So once I have gradients, what can I do with gradients? I can use gradient descent. So far what I have done is, this is my forward pass, this was my model, and this was my forward pass. Okay, so let me do one thing. I'll just take this forward pass out. This is my model, and then this is my forward pass. Okay, and this is my loss. This is the loss computation. Oops, loss computation. And in this case, it is mean square error loss. Okay, once I have this loss, and this is my loss dot backward, this is my back propagation. So I'll put it here. This is my back prop. Okay, so I can also compute loss. I think I should. Once this is actually, this is not printed here, this is all loss already printed here. So loss dot backward is here. Now I'll have to perform gradient descent. Let me show you that gradient descent also. Now I can get all the parameters and take that data and nudge it by some value. Okay, what I can do is, I know how to get parameters. So this is how I can do. I can say for p in model dot parameters, because model dot parameter will give me all the parameters. And then what I can do is, I can nudge the values. I can say for p in model dot parameters, and take all these values, and now I already know that I have p dot grad. For all these things, I have gradient value. For all the parameters class, I have gradient. So what I can say is, I say p dot data, okay, minus equal to or plus equal to, people usually write, well, minus equal to some learning rate. 0.01 is my learning rate, multiplied by p dot grad. Okay, so what is this? This is my gradient descent. This is my gradient descent. Okay, so if I do this now, so I hope the loss will decrease. So if you see loss over here now, so initially the loss over here is 1.2, and if I am printing loss again, in this case, this is 1.2741. Nothing got changed. Okay, this is probably very less. Okay, and we'll keep on doing it. We'll keep on iterating through this process. So we'll see, this is my model, and we don't have to initialize model. Be careful, don't initialize it here. And now we'll perform the prediction again, and we'll see, this is my prediction. Okay, now you will see the loss will decrease. Okay, after this forward pass, you will see loss is decreasing. This is 1.23. I think I don't need loss here because I have to perform forward pass before this. And now again, loss dot backwards. So the question would be, why am I not initializing gradients to 0 before first pass? Because we have coded that in loss dot backward. We don't need to do zero grad. Zero grad is done in backward pass. So I am performing backward pass, gradient descent. Okay, again forward pass, loss computation. Are you seeing now loss increased? Okay, because this is not taking smooth steps all the time. Okay, so I'll keep on doing this. I'll keep on forward pass, backward pass. You see now 1.22. It is sometimes going up because it's saying it might take some wrong steps. Okay, but it is overall it should decrease. Loss dot backward, gradient descent. Again forward pass, again loss computation. Now it is going to 1.19. This is clearly visible over here. This is 1.19. So again taking loss dot backward, gradient descent. Going back, forward pass, loss computation. Now you see loss is 1.15. Okay, then we have loss dot backward, backward pass, again gradient descent. Go back, forward pass, Now loss should again decrease. So 1.1, it is increasing a bit. Okay, but you see that it is taking some steps and it is going here and there, but overall if you see it, it will decrease and then it will become constant. Any questions so far? Okay, let me now write a little bit neater code. So what I can do is just remove all this. What I can do is this MLP is here. I'll define epoch. So epoch basically means take all the data. So do it for all the data. So I was doing it over here. So I am doing it for the epochs now. How many number of times you want to show if you want to show whole the data to your model. So what I can do is I can start with the model. Model is good, and then I'll say learning rate. I'll say LR. So I'll define learning rate over here. So these are my model parameters. So I'll say learning rate is 0.15. And let's say epochs is 300. I want to show this data 300 times to my model. Okay, that I was doing. So what I can do is this is my forward pass. So I will start with for epochs, for these many number of epochs. So forward pass should be performed, and everything should be performed these number of times. For epochs, this is my forward pass. Okay, and after this, so what I was doing is I was doing loss computation. I'll take this line over here. So this is removed. Let's remove this. If you see, oops, I'm just copy pasting. Control A is not somehow working, but because I want to select all, this is not selecting it. This is my loss computation. So I am now doing it for some number of epochs. So epochs I've already defined. Okay, this is my loss computation. So once I compute loss, so I'll perform loss.backward. So I'll paste this code, the thing that we have over here. So I'll paste this also over here. So I'm just cleaning up the code, nothing else. Loss.backward, and then I'm updating gradient. So this is gradient descent. You see 2 lines are there, gradient descent, but we had a couple of classes on gradient descent. You'll only appreciate this once you go through the theory and you yourself code it. So you can see I have done these things so far. For epochs, I'm doing forward pass, loss computation, backward pass, and gradient descent. So I have to also print. Suppose I'll print loss after some epochs, and then we'll see if loss is decreasing. So I'm saying for epochs, if in every 50 epochs, you should show me the loss that you have. Okay, and at the end we'll show the predictions. So after the model is trained, say for so 300 epochs that we have defined, we will see what are the model predictions. Okay, for x and y, yp, this is my x and this is my y and this is my y prediction, and I want to see what is the input and what is the target that we have to do. Okay, so this is what I've defined. So I'm again initializing this is my data, this is my model and learning rate. Okay, and for 300 epochs we'll see what will happen. So you see loss is decreasing 1.87, 1.53, 1.28, 1. This, it is going to decrease, but loss is still high. But you saw the prediction was 0, and you can even run it more. You can keep on running it. We'll see 9.94, and it's tapering off 9.92. The model initialization was bad. You can see that this is going up. So you see we want this as -1. This should be 1. But these predictions are like quite bad, I suppose. Maybe initialization. Let's do this. This is 1.08. Maybe we have to train this model more. Oh, okay. Learning rate here is. I have to also paste this learning rate, not the learning rate that we had. We're taking very small steps. We want to take a little bit larger steps. Let's do one thing. Initialize the network again. 0.96. It started from 1.8 and it went to 0.96. The predictions are still bad, and you have to keep on doing it. And this I can say for say some 1000 epochs. You can see this. The loss is tapering off. Somewhere the loss is not going there, but the predictions, if you see, this is -0.1, 0. This is very bad. We might have to see the network. So if you see this, there is some indentation or some error in operations. You can just thoroughly verify these things, but this is the correct version. So the earlier version that we had, there is some minor issue that you can clearly see somewhere. And then if you see this, I'm running it for say 1000 epochs. Okay, this is my training loop. So I'm saying MLP, creating an MLP learning rate, 300 epochs. And then once I'm running, you can see the loss is going down continuously. And you can see this is my target should be -1.0. The prediction is 0.932. It's very good. And this prediction is -0. And this is -91. And you know, this is also very close. And if I increase the epochs, the result should increase. So if I say 1000 epochs, again you can see this is minus 9.96. This is very good. Okay, and losses kind of decreasing. And how can I do? You can also plot this losses against each epochs. Okay, you will take epochs on one side and loss on the y-axis, and you can use matplotlib to plot this loss. Okay, this I am showing it by numbers, and you can also plot it visually. This is how you train network. Again, you are showing you the training loop, so you can see this. You are defining a model. Okay, then you are having some learning rate, you are having some epochs, and for each epoch you are doing this forward pass. Once you are done with forward pass, you are doing loss computation. Loss computation is telling you how bad or good is your model, the model that you have currently. And then you are performing this backward, and in backward we don't need to zero grad because we are doing it in the backward pass. And then for each of the parameter you are performing this gradient. This is your gradient descent. Okay, this is your forward pass, loss computation, backward pass, gradient descent, and this is just for printing purposes. And once you are thinking that now losses decrease, and this is your last final prediction, and these are predictions, and you can see the number of epochs as I increase them. You can clearly see this is getting closer to solution. Okay, I think this is what we have trained. We have trained our first network. The case that we had is XOR cannot be modeled by a single perceptron. If you have a perceptron, you cannot model XOR function by this. Now we use multi-layer perceptron, and you saw that it can easily model this XOR function. This is one example. Let's do a little bit more complex example, and then we will wrap up this, and then you will be given chance to implement it for your own example. Okay, let's do it for maybe a couple of examples. I'll do it for 2 examples, which I had written code for. I'll just copy paste it. So I'll do it for Moon dataset and Iris dataset. Iris dataset has been introduced in machine learning classes. So if you see, so I have sklearn in the datasets, I have make moons and load iris, and I'll show you how these datasets look like. So what I can do is I will say I'll just import this, and after this I'll paste. You can see I am creating synthetic dataset. This is X synthetic make moons. This is a dataset which will be of 100 samples, and I'll show you how dataset looks like. And this is a real dataset. Iris dataset is a real dataset which has classes setosa, and we are having versicolor. Now using this sepal length and width. So this is what we have. So you know that in the dataset we have 4 classes. Okay, setosa, versicolor, virginica, and some other class. And we have also petal length, petal width, sepal length, sepal width. But here we are taking sepal length and width, just 2 features, and we have to just classify setosa and versicolor. And this is our iris dataset. Okay, and this is idx is less than 2. Basically I'm just taking classes 0 and 1. So I'm taking x real, this is my x features, and y is my class label. And here this is x synthetic and y synthetic. Make moons basically is a dataset that I'll show you. Before this I'll plot the dataset. Let's plot that. This is the dataset if you want to see. So I'll just copy and paste plotting code. It should not be difficult for you people to understand. Just pause the video over here, and this is just basic plotting. Take x and make a scatter plot, and these are just feature 1, feature 2. So if I just show you the moon data, say I'll show you some data set like moon data, because we have 2 data sets now. If you see this data set over here, we have 2 data. We have synthetic moons and we have iris. These are 2 data sets that we have. So what I can do is I can just paste it over here. I can say plot data. Data sets is not defined. Let me run this cell. NP is not defined. Let me run this cell also. I'm forgetting to run cells. Okay, now if you see, these are 2 data sets. We have moon. So this is looking like this is one class and this is other class, and you can clearly see this is non-linear. And here this is sort of a linear boundary. So here if somebody draws here boundary, this is a linear boundary, but this is for non-linear. So this is more interesting case. But we have 2 data sets. So one thing was synthetic moons, and you can clearly see I loaded it from dataset that is sklearn, and iris also has this iris also is available in sklearn. I'm taking the data sets. I'm getting features and the corresponding labels. We have 2 classes in this make moons, and we have 2 classes in load iris. So in the 2 classes we have is setosa and versicolor, and the features that we have is sepal length and width. I think people are clear with this because we have seen this in machine learning. And here we have class +1 and -1. That's same. And now I'm also writing plotting code, and this is how plot looks like. So for this I want a decision boundary. Let me just show you how decision boundary should look like in this case. Okay, so in this case I want decision boundary to be something of this sort. Okay, something of this sort should be decision boundary, and this should be red class, and this should be my blue class. The decision boundary should look like this, and I can use the same network that I used. Okay, here I'll introduce more concepts like batching and stuff like that. That's why I'm showing these 2 examples. Okay, so what I can do is I'll start now training the same thing that I did over there. I can do it from here. Okay, let's train it. The first thing is we'll do learning rate, and we'll have our learning rate and epoch. So again, learning rate is 0.15, epoch is 300. Now we'll have batch size because we have many samples over here. So in one of the, so we'll perform epochs. So in epochs, I'll not take the data set as a whole, what I can do is I'll take some batch. Let's say I'll take 16 examples. So I'll say batch size over here. So we'll perform, which is called as mini batching. So we'll take mini batch. So let's suppose samples are say 200 samples. I'll shuffle the data set and then I'll take 16 samples out of that. So now what I'm doing is I'm just writing a for loop because I'll do it for both data sets together. So I'm saying for name x comma y. So I'm doing it for both data sets together. So if you see this for name x comma y in data sets, and I'm doing it for both of these, and I'll get x and y. I'll prepare my data first. Okay, before this you'll have to pre-process everything your data, but assuming that data is pre-processed, this is my xs. Suppose now I'm working with say moons data set. So when I'm working with that, so what I will do is I'll take features of that and label corresponding target label. So this is how I'm extracting it. For that data set, take 2 features and make them as params, and also the target also should be params, and then I'll make a model. The model that we already have, we'll use that model. So model is this. So I'm making 4 layers, 3 layers, 4 neurons for first 2 layers and 1 for the last layer. So this is my model. So model is MLP, multi-layer perceptron, 2, 4, 2 is the input because we have x1 and x2 feature, 2 inputs. Now I'm doing mini batching. So the number of samples I can calculate is from length of how many, because I'll have a lot of examples over here in this case. So I'll take mini batch. So I'll say this is the total number of samples that we have. So now I'll do it for number of epochs. So if I can paste the code over here, you can see I'm saying for epochs in range of epochs. So this is number, suppose here we have 300 epochs, but I'll do it for batches now. The initial what I'll do is I'll shuffle the indices. I'll shuffle the whole data set because I don't want to create any bias. So I'm shuffling the data sets. How to shuffle that? You can see indices is equal list of range of n samples. So I'm creating an list of indices. So indices will be from, it will be from 0 to, suppose we have 200 samples, 0 to 200. This is the indices. Then I'm shuffling the indices. I'm saying shuffle these indices to all together. So you can have 0, 8, 12, 13, 14, and I'm shuffling it. So once I'm shuffling it, now I'll use the batch. So I'm saying for start, so I'm saying for start in range of 0 to n number of samples. So go from 0 to n number of samples with this batch size. You know how for loop works. I don't have to explain you this. So take these n number of samples are then total, but with batch size you have to shift by, suppose in this case 16. So if you say from 0, you'll take from this indices, suppose you'll take this, you'll take 16 samples in each case. Okay, and now indices are shuffled, so we won't be skewed. So you'll take batch indices, and it will start from start and end from start plus indices. If you're not understanding, please let me know. I'll just copy one more line of code and I'll show you what is happening. So I'm saying now batch index. So which batch am I taking? So from this indices list, because indices is containing another list of indices that we can use to index in this data that we originally have. I'm saying indices start. So I'm saying start it from the start, wherever you are from, and then just shuffle it to the, make sure that you are taking number of samples you got batch size. I'll just make a diagram so as to make you understand this. So in this case, if you see, so here these are indices. So we have say 200 samples. So 200 samples are there. This is my data set which we X that we have 200 samples. So now I'm saying make indices. So indices will be a list. It will be like 0, 1, 2 till 199. So this is my list of indices over there. This is what this is doing. And now I'm shuffling it. I'm randomizing this. Okay, what I'm doing is I'm saying 0 is here, 1 is here, 200 is here. So I'm shuffling these indices. Okay, initially I had, this was from 0 to 200, 0 to 199, sorry, 0 to 199. And now I'm shuffling it together. So if shuffle happened, so you will see that all of these indices will get randomized. So once this is randomized, now I'm saying for start, I'm starting from 0 to n samples. So 0 to n samples basically mean these are 0 to 200 samples. I'll have to go to 199. Suppose here we have 0 to 200. So 0 to 200, but batch size is 16. Okay. So what will happen? This will run for say 200. This will run for all the samples, this loop. But it is taking 16 batches. So it is saying batch is equal indices. Take it from start. Say the start indices right now. I'll start from here and then do it for 16. So it will take the first window, 16 window, and next time it will take other 16 samples. Next time it will take other 16 samples. Okay, it will take all the 1600 points. Okay, this will be called one step. So this is one step. Within epoch you have steps. Okay, one step contains 16 samples, and that's our batch. So it will roll the window. You have 16 and then 16 and then 16, and it will do these number of epochs till it covers all the samples in the batch of 16. I hope this is clear. This is clear so far. So what I'll do is now I'll perform. I'll take batch of this. I'll now prepare my data. So this is my data now. So if you see, this is my data. So this was my batch index. So now I'll use this batch index. I'll get batch access because I'll use this index to get it from the xs and ys, that is the original features and the original prediction. So this is my batch now. Okay. And after I have this, I'll perform forward pass. Forward pass is pretty easy, not difficult. and then I'll also perform loss. So what I'll do is, so I will do this. So I'm saying I'm doing forward pass, and you know how to perform forward pass. You use this model of x for x in batches. So you'll have this x in batch, you'll perform a prediction, and then you have this batch ys. So for this batch ys and y, this is my ground truth and this is my prediction, and I'm zipping them together and computing the mean square loss and then computing the whole loss together. And then what I'll do is I'll do zero grad, which is not required because I'm already doing it in backward pass. So I'll do that loss dot backward, because backward pass is implemented in such a way it does zero grad. Okay, so this is loss dot backward. Okay, now gradient descent. Now this is stochastic gradient descent, SGD, because we are taking batches. Okay, you have this, this is SGD. This is stochastic gradient descent. I'm taking some batch size 60 and then I'm doing it for that. And now I'm again printing the same thing. Okay, again printing. The epoch is this and that. So I'm saying, say if epoch is at 50, then print these predictions. Okay, it'll basically show me the loss. And after that, I can also visualize the boundaries. And for that, I'll have to write the code first. Let me see if I have written the code for visualize boundaries. Okay, I'll copy paste the code, and I think matplotlib has been done. So you should be well versed with this. So I'm just adding one more cell over here. So this is plot boundaries, and I'm also doing it for PyTorch. So I will also import PyTorch somewhere, because I'll compare all the things that we have done so far in PyTorch also. We'll compare this with PyTorch also. Import torch. Okay, I think now this is the code that will plot the boundaries. Okay, not so difficult. You can just pause over here and then you can understand this code, because we have done a lot of matplotlib. So here, now if you see, this will do it for both datasets together. So if I again show you the code, this is going from datasets, because we have two datasets and it is extracting data from both of these, and then we are creating a model. Model is pretty simple. Okay, we are creating number of samples and number of epochs is already there, and we are doing it for batches. Now the batch thing is over here. So you should understand this pretty easily. I have tried my level best that you could understand this. So if I'm doing a forward, backward, and SGD, and then I'm printing for the epoch. So if you see this over here, so loss, if you see, so loss is going down. So after 300, loss is 0.05 something, 0.03. Okay, now we can plot the boundary. So if I show you boundaries for both of these, okay, let me plot the boundaries for both of them. Okay, model x and y. Maybe I will plot the boundaries after this. Okay, let me again retrain the model and plot boundaries, because model is trained now. So I can use any data set. So maybe I can use it here. So this is plot boundaries. This is my model, and I have to use the data set that I had. So say x of 1 is my first data set, x of 0 is my 1, and then at the second is x of 1. These are the two boundaries I'll plot. Too many indices. Let me just put it in the villa and retrain. Give me a second. I'm just pasting it and deleting this code. The same code, I'm just pasting it in different cell with this visualize boundaries within the code. So once this is done, so it will automatically plot this, because I don't need to have x and y separately. These should be data sets. So if you see this now, so this is the first moon data set. You can see this is the decision boundary, and this is the real iris separate data set, and this is the decision boundary. It did a pretty good job, but you could have still trained it. We don't want to overfit again, so we don't want to make sure this point also gets classified correctly, so it will overfit. So you can see both of them are pretty clear, and this is whole of this thing was done by using our own mini PyTorch. Okay, this is our original data set, and after that we wrote training loop. So in this training loop, if you see, we did batch of 16, and after that you can clearly see that this was able to classify these points pretty accurately. Okay, and you can also now say this is class 1, class 2, and you can see you can compute accuracy and all that, so you can compute different metrics. Okay, and I could have made this loss function much more, I could have added regularization, but we have not studied that so far. But the first thing we'll do, we'll also compare this thing with PyTorch. So for this case, we took XOR. So XOR will do the same thing with PyTorch, and we'll see if the PyTorch works something like similar. And that will be the last topic, and then we are done for the day. Let me do it for PyTorch. Okay, I just copy and paste code and explain you the code. So this is the loss for, this is my XOR. This is XOR, and I'll do it for PyTorch. So if you see, this is how torch code will be written. import torch, torch.nn, torch.optimization, because we have torch, in that you have a neural network, you have these optimizers also. So this is how you define a multi-layer perceptron in PyTorch. In our case, we define it our own way. So here they are saying nn.linear. You have a linear layer, input is 2 and output is 4. After that, apply the activation function. Okay, and again define one more linear, that is, it will take input 4 and output 4. So this is actually our network 2 4 2 4 4 1. 2 is number of input, then 4 neurons in the first layer, 4 in the second layer, and 1 neuron in the last layer, and we're applying 10H continuously. Okay, and then we're also initially it won't match because we have to make sure that seed and everything is there, but here I hope it will not match. Okay, and then we are performing forward pass, and this is our X data. So this is 0 0 0 1 1 0 1 1. So this is our data. Okay, this is why this is the XOR, minus 1 1 1 minus 1. Minus 1 here in this case means 0. And then I'm saying model is this model. I'm initializing torch MLP. So this is my MLP that I have created by using torch, and optimizer is SGD. Okay, so I'm using SGD, and this is the model, and this is the parameter, and I'm also having learning rate, so that I'm defining, and then I'm doing it the same over here. So you can see if I run this, so the predictions are pretty much similar, and even our model is more accurate with, I think, with 3. We'll see. We are having more. I should not give benefit of doubt to myself. So 300 epochs. So it starts with 1.6. It's going, but you can see how slow our model is and how fast PyTorch is. Why is our model slow? Because we have to perform a lot of optimizations. Oh, why is it performing still this? Oh, okay. Did I run this cell? It's still going for 1000 epochs anyway. Let it go. 750, 800, 950. You can see these are prediction. Oh, this is the data is different. Is it? No. Let me see. I'll have to define it from data also. So neuron layer. This is my data. This is my XS. This is my model. Yes, this data was different. Sorry. So now we can take number of epochs is not 1000. It should be 300. Okay, we have defined it multiple times. Let me delete this now. I don't need this cell. Okay, so this is my data for XOR. This is my custom model that we have done, and you can see 0.03. And now if we run PyTorch is very good. Our model is giving way better answer. So you see this is giving minus 0.92 and this is giving 0.94. Okay, it should be minus 1. Our model is closer, and this is minus 9451 9051. Our model is performing better than PyTorch, but still you can see that they are giving pretty much similar answers. The PyTorch is doing the same, but you see the even API, the API that we are using for PyTorch is pretty much similar that we have done. So in this case, we are making linear plus this, because in our neuron we have already defined the activation. We could have just taken that out and then defined it separately on the neuron. You could also do that, okay, to match the PyTorch API. But in our case, we were just defining a layer, and with the neuron was already 10 activated always. Okay, so in our case, we only supported 10H activated neurons. So here they support a lot of activated neurons, but you see this, they have torch, they have defined NN. So you can also folder wise organize the code in the similar fashion. Torch.optimizer, they have a lot of optimizers defined. So here if you see, the optimizer defined was SGD. Okay, so in our case, this was the code. This is our code for optimizer. This is what we used gradient descent. But you can clearly see that the way PyTorch is doing and the way we are doing, the answers are pretty much agreeing, and our model is performing better, maybe because of initialization. I should not give benefit of doubt to us. Maybe our initialization is way better than PyTorch. Okay, but PyTorch will be way faster than what we have done. I showed you that even if I take some other data, suppose our XS was the data that was this, like more samples, our model will take much more time to train this, the data that we had. Okay, here we are doing batching. So let me do one thing. Let me again, this is my data. Okay, let's create this data. So this is my data, and I can take access from this. So say, let me run this. Okay, because I want that data. Okay, let it run. So you can see how much time is it taking. If I do this in the PyTorch, it will be very fast. Let me do that in the PyTorch. If I have that code written with me, I suppose it should be there. Yes, PyTorch will do it very fast. That is what you have to optimize the code, because PyTorch is mainly written in C++. Okay, so if you do this, so I am doing the same thing that I did now for these two data sets. Now I had data set, so torch MLP, and doing the same things. Torch.tensor is this, y is this, data load, because we have data loaded there, we have all these things are there, but here we were manually loading data. So in Torch, you have this tensor data load, you have tensor data set, and then you have data loader, and then I'm initializing model. This is my mean square loss function. Everything is almost similar, but we defined everything by our own. Here you just call these APIs, okay, which I generally hate if you are learning, but you should use them if you are writing a production grade code. Okay, so you should not then use micro whatever we have written, micro PyTorch or mini PyTorch. So if I now run this, you'll see how fast this is. This is very fast. Okay, it is doing for both of the cases. So in our case, it was taking almost double time. So how many of you are able to understand the whole thing? So what we have done is we have also did similar thing like PyTorch. Now what your job is to take this code and you should organize the code and you should see what are the possibilities where I can optimize this code. Right now it's written in Python. As I said, PyTorch is probably like 10x faster or maybe more than that. Why is that? Because PyTorch is written in C++. And C++ is very close to hardware. It's performing way better than we have written. But the functionalities that we have added in our class, this is the base thing that PyTorch would have done. But these are very well maintained. These frameworks like PyTorch or TensorFlow, they are very well maintained, and there are like thousands of people working on these things. So they have the compute and they have the manpower to do this. But here we have like 10 people. So if you people will take the code that we have written right now and you can refactor the code and see if there are possible optimizations, if you can do that. So now it is becoming an engineering problem. Initially it was a scientific problem. So where we understood everything, where we said, okay, it is possible, we can do this, we can train the network. So we are done with the scientific problem. Now it becomes the engineering problem. Engineering problem is where you will take this problem, you will optimize the stuff. So as I always give the example, suppose NASA initially landed on the moon and it took them a lot of cost. Now India also landed on the moon with very less cost. The first thing is when you have to do the scientific problem, you have to show it as possible. To do this, it is possible. You have to show it mathematically, theoretically, and then you do something and it takes a lot of cost. And after that, you have to perform engineering on that so that you will optimize the stuff. You will make it more efficient. You will reduce computational complexity so as to make it faster. So this is the problem that will now befall on you. You people have to take this code and reorganize it and keep on adding functionality to it. So I showed you what we have done is we have just one type of neuron which is tan H activated. So what you can do is you can remove the tan H activated neuron from this. You can just make a neuron and separately apply activation onto that. Okay, you can apply you can have a separate layer of activation. You can have a module of activation functions as we have in PyTorch. So if you see in PyTorch, here I suppose it's here. So you can see we applied nn.tan H. So initially we had linear layer. So it is just layer of neuron. It will perform just forward pass. It's not giving. It's performing forward pass without activation. It's performing affine transformation. But after you apply this nn.tan H, it is applied on each of the neuron. Okay, and then linear, it's again applying tan H. The possibility here is that you can have different activation functions for different layers. But in our case, we have just did tan H activation, so you will have to change that. Okay, but if you see, but still our model was performing okay-ish. Okay, and even sometimes better than PyTorch because of the initialization. But PyTorch was way faster. Any questions so far?